අපි අද කතා කරන්න යන්නේ today we are going to discuss about the lattice enthalpy first, right? This is the page number 5 of etude. Lattice enthalpy, right? After learning the lattice enthalpy, we are going towards the Born-Haber cycles, right? That is some major part today to discuss, right? Okay, so standard lattice enthalpy, our first enthalpy term to today's discussion, right? That is number 10, standard lattice enthalpy, right? So that is delta H naught L, or one can say LE, that is energy, right? So we are going to discuss about two enthalpy terms here. One is standard lattice dissociation enthalpy, the other one is lattice formation enthalpy, right? Two enthalpy terms are coming under lattice enthalpy, right? Yes, let's start with the standard lattice formation enthalpy, right? Lattice formation. Right. So lattice formation means actually we are supposed to start with the constituent ions. So starting up with the constituent gaseous ions, we are supposed to form 1 mole of solid ionic lattice, right? That is what referred to as the standard enthalpy change of lattice formation, right? Starting from the constituent gaseous ions, we are supposed to produce 1 mole of solid ionic lattice, right? So 1 mole should stand with the solid ionic lattice, right? 1 mole should stand with the, right? So we are supposed to produce 1 mole of solid ionic lattice starting from the constituent gaseous ions, right? So definition is given, just go to the definition there. Enthalpy change when 1 mole of a solid ionic lattice is formed from its constituent positive and negative ions at the standard state. It should not be at the standard state. It should be that's okay. Constituent gaseous, that gaseous term is there, right? So anyway, it's constituent gaseous positive and negative ions at the standard state. It's okay, right? First highlight the stuff, the most important ones there. That is 1 mole of solid ionic lattice is formed. Let's highlight that stuff. That is where the 1 mole stands. So when studying enthalpy terms, that is what we do, right? We just concentrate on where the 1 mole thing appears, and then we need to know about the chemical species or know about the species appearing at the other side of the equation, right? So 1 mole stands with positive and negative ions. Sorry, 1 mole stands with the solid ionic lattice, and the other side of the equation should contain gaseous positive and negative ions. Just highlight that thing as well. Constituent gaseous positive and negative ions, right? That phrase. Constituent gaseous positive and negative ions should be at the other side, right? So let's come up with that this example. So some example is given in your note for the standard lattice formation of NaCl is given, right? Given as minus 788 kilojoules per mole. That value is given. So remember, if you are thinking of a lattice formation, if you are discussing of a lattice formation, those values should always be negative values, kind of exothermic values, right? Exothermic values. Why is that? With the lattice formation, we are discussing about bond forming. We are discussing about bond forming. Starting from the gaseous positive and negative ions, you are trying to form 1 mole of solid ionic lattice. So kind of bond forming there. Bond formings are exothermic, right? So always the lattice formation enthalpies are coming up with minus signs because those are always exothermic. See how to write this equation? So how to write the thermochemical reaction for this thing? So you are supposed to form 1 mole of solid ionic lattice. So solid ionic lattice, that is where the 1 mole stands. That is, we are the one more strands, right? We are supposed to form that thing starting from its constituent gaseous ions. So constituent ions of NaCl is the Na plus ion and the Cl minus ion. Na plus ion and the Cl minus ion. Those are the two ions of NaCl. So you have to start with the constituent ions, but at the gaseous state. This gas is very needed, right? Solid ionic lattice is to form starting from its constituent ions at the gaseous state. This should be at the gaseous state, and this should be a solid ionic lattice. These are the most important stuff when concerning kind of a lattice enthalpy, right? So starting from the constituent ions. So you have to balance this stuff, keeping here the number 1. So 1 sodium, 1 chlorine, right? The things are balanced. So have to start with constituent gaseous ions, right now? Okay, this is the lattice formation enthalpy, always coming up as a negative value as we are discussing about bond forming, right? Ionic bond forming in this case, right? So what about the next one? That is dissociation. Both are the same thing, but the opposite signs, right? If you think of the lattice dissociation, so then we are discussing about dissociation of bonds, dissociation of ionic bonds in 1 mole of solid lattice, solid ionic lattice, dissociation of the ionic bonds in 1 mole of solid ionic lattice to their constituent gaseous ions. The opposite of this thing, right? Dissociation of all the ionic bonds in 1 mole of solid ionic lattice, that is where the 1 mole should stand with the solid ionic lattice, right? To come up with constituent gaseous ions, right? See, go to the definition there. It is said for the lattice dissociation, enthalpy change when 1 mole of solid ionic compound, right? Solid ionic compound, or one can say solid ionic lattice, right, is converted to its constituent gaseous positive and negative ions at the standard state, right? Okay. So you can just highlight the important stuff there, where the 1 mole stands. First of all, 1 mole of solid ionic compound. So you have to highlight that thing. One can say solid ionic lattice, right? Then at the other side, constituent positive and negative ions. Constituent positive and negative ions, right? So if you think of the same example as a dissociation, standard lattice. In this case, that thing is not given, just lattice enthalpy. So lattice enthalpy of, right, NaCl. If that value is given as a positive value, if the lattice enthalpy value is given as a positive value, that means it is all about bond breaking, endothermic, right? So positive values means kind of endothermic, bond breaking, endothermic, that means bond breaking, right? So this is all about lattice dissociation. Right? Here the negative value is given, that means exothermic, that means it is all about lattice formation. Right? The positive value means it is endothermic, that means lattice dissociation. So they can give the lattice enthalpy as a positive value or a negative value, right? Depending on the sign, you have to decide right? Whether it's the lattice dissociation or the lattice formation, right? That is what you need to learn from here. So here the lattice enthalpy is given as a positive value. Positive value means it's an endothermic value. That means they are discussing about lattice dissociation, bond breaking. Endothermic things are means bond breaking things. Bond breakings are endothermic. So if they have given you the lattice enthalpy value as a negative value, lattice enthalpy value as a negative value, that means it's kind of an exothermic value. Exothermic values are coming up when the bonds start to form, lattice formation, right? So by looking at the sign of the lattice enthalpy they have given, you have to decide whether it's a lattice dissociation or a lattice formation, right? Okay. So if you write the reaction here, this is a positive value, that means lattice dissociation, right? Lattice dissociation means you are supposed to break or dissociate ionic bonds in 1 mole of solid ionic lattice. In this case, it's the NaCl, right? To come up with its constituent ions at the gaseous state. So the constituent ions are Na plus and Cl minus. Those should be at the gaseous state, right? No? So gaseous ion, right? No? Okay, that is the lattice dissociation. So you have two examples. I mean, two exercises to do. Just go to that. They have asked you to write down the thermodynamic equations for a lattice enthalpy of magnesium chloride. First thing is given as a positive value, and second thing for the lattice enthalpy of aluminum oxide, that value is given as a negative value. So just come up with the two thermochemical reactions related to those, right? This is delta H naught L of magnesium chloride. No? The value is given as a positive value. The second thing, aluminum oxide. Right. Let's try to come up with the thermodynamic equations here. හරිද බලමු. So write this one. So this is given as a positive value, endothermic, that means bond breaking. This is about dissociation then. This is dissociation, right? So that means you have to dissociate the ionic bonds, right, in 1 mole of solid magnesium chloride to come up with its constituent ions, right? So solid magnesium chloride 1 mole is converted to its constituent gaseous ions. Those are the magnesium 2 plus Aq, sorry, gas, right, gaseous ions, right, and Cl minus, those are the constituent ions there, Mg2 plus and Cl minus, and you should have some 2 of Cl minuses, right, and this should be 1, as that is where the 1 mole stands with the solid ionic lattice, right. For the mass balancing you need some 2 here, right. So this value is given as plus 2, 5, 3, 4. What about this thing? This is coming up as a negative value. That means it is exothermic. Exothermic means bond forming. That is formation. Right? So that is formation of aluminium oxide. So that means starting from the constituent gaseous ions, you are supposed to produce or form 1 mole of solid ionic lattice, right? Okay. So constituent ions are aluminium 3 plus and O2 minus, aluminium 3 plus and O2 minus. So starting from this, you need to form 1 mole of solid ionic lattice, right? Now you need to balance the stuff. This is where the 1 mole stands. So you need to have 2 aluminium species and 3 oxygens. So that is how the things will be balanced, right? This value is given as minus 6 kilojoules mole. Right? No? Okay, that is how we are supposed to come up with the right two thermodynamical equations there. Right? That is done. Okay, before going to the 11th and 12th and the rest of the right enthalpy terms, let's go towards the Born-Haber cycle, which is appearing at the page number 9, right? So this is another form of thermochemical cycle, right? This is another form of thermochemical cycle, right? Born-Haber cycles, but this is a bit complex than the normal thermochemical cycles. Normally, thermochemical cycles involve 3 or 4 right states, no? 3 or 4 states of the same system will be discussed normally with the thermochemical cycles. But when it comes to Born-Haber cycles, you may have few more. You may have 5, 6, even 7 right states of the same system, right? Okay, let's try to come up with Born-Haber cycles, right? First of all, we are to draw the Born-Haber cycle of NaCl, right? Let's start with that. Let's learn how to draw a Born-Haber cycle, taking a NaCl as an example, right? So Born-Haber cycle. Of NaCl. Let's try to come up with this thing. Right? When drawing Born-Haber cycles, right? When drawing Born-Haber cycles, right? The first thing to do, right? First of all, just know that Born-Haber cycle actually represent different states of a same system, right? Different states of a same system. So what is your system? Your system is NaCl. That means throughout each and every state here, right, only one sodium atom and one chlorine atom should appear, right? Throughout all of these states, I am going to draw here. Only one sodium and one chlorine should be there, because this system contains only one chlorine and one sodium. So I am trying to draw different states of the same system. That is what we represent as a Born-Haber cycle, right? So we are starting with, normally when drawing Born-Haber cycle, we are starting always with the reference forms, the reference forms of the system. So this system contains Na and the Cl. The reference forms are: sodium's reference form is Na solid, chlorine's reference form is Cl2 gas. So always start drawing the Born-Haber cycle with the reference forms of the constituent elements, right? So we have to come up with some half here, as we are dealing with one sodium and one chlorine in the system, right? Alright. So always you are starting up with, I'll write it here, reference forms. right? Next one, after that we draw at the bottom like this the solid ionic lattice, of the system, that is NaCl solid, right? Solid ionic lattice or solid ionic compound will be written secondly. So these two things are with a relationship. What is that relationship? That is actually the formation enthalpy, right? We can connect these two states of the system by the formation enthalpy. By this formation enthalpy. If you come from here to here, that is all about delta H naught. If starting from the reference forms, you are forming the compound, 1 mole of compound, right? Third thing, when drawing a Bornholm cycle, is coming up with the constituent ions of a system. So what are the constituent ions of this thing? Na plus and Cl minus. Gaseous forms, gaseous constituent ions. It is the third thing to mark in a thermochemical cycle. Normally in this kind of a place we mark that. Constituent gaseous ions. So we know the constituent gaseous ions and the solid ionic lattice 1 mole is related with the standard enthalpy change of lattice or standard lattice enthalpy change. Delta H naught, actually this is lattice formation. One can write the arrow other way around as lattice dissociation as well, right? Okay, these are the first three things to draw when drawing a drawing a Bornholm cycle, right? Then we have to connect. We have to convert this sodium solid, the reference forms, to these constituent gaseous ions. That is the next stuff to do. We have to convert the sodium solid, the reference form of sodium, to Na plus gas, as well as we need to convert the Cl2 gas, the reference form of chlorine, to Cl minus gas, right? To do so, definitely we know we need the help of the ionization energy as well as the electron gain energy. The positive gaseous positive ions are formed by with the use of first ionization energy. The gaseous negative ions are formed by with the use of first electron gain energy. So ionization energies as well as electron gain energies, ionization enthalpies as well as electron gain enthalpies are involved, should be involved to produce the gaseous positive ions and the gaseous negative ions, right? So you have to keep that in mind. To come up with the ionization energies as well as electron gain energies, right? First we need to actually come up with the isolated gaseous atoms. So ionization energy means actually isolated gaseous isolated gaseous atom is releasing electron to come up with the Na plus gas. That is what ionization, isolated Na gas giving off an electron to come up with the Na plus gas. That is what ionization means. So isolated gaseous atoms are needed to do ionizations as well as electron gains. What is electron gain? Electron gain means isolated gaseous atom gaining an electron to come up as 1 minus gaseous ion, right? So if you are thinking of chlorine situation, chlorine first electron gain means chlorine gas, the isolated gaseous atom, accepting an electron to come up as Cl minus gas. So to come up with the ionizations as well as electron gains, first of all we need to come up with the isolated gaseous atoms. So that we need to convert these things to isolated gaseous atoms before we are to apply the ionization as well as the electron gains, right? Okay. So converting this into gaseous atoms, that can be done by sublimation enthalpy. Sublimation enthalpy, right? So converting or converting this into here, right, can be done by few methods. One is you can apply the sublimation enthalpy. If you apply the sublimation enthalpy, solid will directly convert to gas. Or you can apply atomization enthalpy. Atomization means what? Reference form will convert to 1 mole of gaseous atoms. Atomization. Reference form will convert to 1 mole of gaseous atoms. Can apply that thing as well. What else? What else? You can apply the fusion and then the vaporization. If you fuse this stuff, sodium solid converts to sodium liquid, and if you have to apply the vaporization, that will liquid will convert to gas, right? That way as well you can convert this solid to gas, right? Delta H naught, what? The fusion plus that, right? So one out of these three methods can be used to convert the Na solid to Na gas, right? When that happens, nothing happens to this thing, that thing will be there as it is, right? So now we had converted the solid reference form of the sodium to its gas, so that now we can apply the right ionization stuff. Now we can apply the ionization, right? We can convert this into sodium plus gas by releasing a neutron. This is what? This is the first ionization. So before applying the ionization, so it is a must to come up with the gaseous form of the atom. So with the solid form you can't do the ionization of the electron gains. First you need to convert that into the gaseous form, then only the ionization and the electron gains can be done. I1, this is I1, first ionization, right? So nothing happens to this thing, that will be still there. This is all about different states of same system, so that definitely one chlorine atom should appear and one sodium should appear with all these states, right? That is why we need to write this thing as well, right? Those are done. Then now we will convert the chlorine thing to Cl minus. For that, before applying the electron gain to come up with the Cl minus, first you need to come up with the monoatomic gaseous form. Not only the gaseous form, but the monoatomic, isolated gaseous form is needed. Not like this. Cl2 form is not preferred to do the ionizations and the electron gains. This monoatomic gaseous form, monoatomic gaseous form. Diatomic thing is not preferred, right? So first we need to convert this thing to monoatomic gaseous form, right? Like this, right? Monoatomic gaseous form, only just one chlorine is appeared, right? So that can be done by doing a bond dissociation or a atomization. So by doing atomization you can do, the reference form can be converted to the gaseous 1 mole of gaseous atoms by just applying the atomization. Or if the atomization data is not given, what we can do? We we can come up with the bond dissociation. Bond dissociation means like this, no? So here you have half a mole of gaseous covalent bond. Half a mole of gaseous covalent bond, not 1 mole, because this half a mole of gaseous covalent bonds. So you have to break only half a mole of gaseous covalent bonds to come up with Cl gas. 1 mole, right? That means half into delta H naught bond dissociation. 1 into atomization O, half into bond dissociation will give you 1 mole of gaseous atoms. See, when applying these things, if you are going with the atomization, always use the stoichiometric value here at top. If you are going with the bond dissociation, always use the stoichiometric value here. Simply as that. So these things will appear without a change. Right? Then finally, now we can gain this electron to Cl gas, right? Cl gas gaining this electron will convert to Cl minus gas. That is all about electron gain. First electron gain. Right? This is your Bornholm cycle of NaCl. Right? No? Okay. You can apply the Hayes' law. You can apply the Hayes' law to find out any of these enthalpies if all the other enthalpy values are given. If all the other enthalpy values are given, to find out any of the missing enthalpy term, you can use the Hayes law. You can apply the Hayes law to this one, right? You can use the Hayes law relationship coming from this diagram, right? So if you are compared with the Hayes law, apply the Hayes law for this. So this is the initial state and this is the final state. This is the initial state, this is the final state. So we have two roots. This is one root, the direct root, and this is the second root. So delta J to F, the enthalpy change occurs with the first root is equal to the enthalpy change occurs with the second root. As long as the initial and final states are the same, the enthalpy change is same, right? This root is equal to this root, right? So I'll come up with just one, using just one term here, right? Plus this one, I come with bond dissociation here, plus this thing, plus this, no? Right? This is the Hayes relationship with this term in cycle. So you can use this relationship, right, to come up with any one of these terms if all the other terms are given, right? Now, right, this is all about the Bornholm cycle of NaCl. Now I just try to draw the Bornholm cycle of magnesium bromide as well. Magnesium bromide के Bornholm cycle के तनिक मतलब लेना वाटा. Just draw that. Magnesium bromide के system में Bornholm cycle के अंदर लेना वाटा. Always I just start with the reference forms, then come up with a solid ionic compound, and then come up with the constituent gaseous signs. Then think of converting the reference forms to the constituent gaseous signs. හරි මුලින්ම පටන් ගන්නමයි reference forms වලින්. හරි. So magnesium bromide system reference form එකවත් reference forms. Right? Reference forms of the magnesium bromide system. So magnesium's reference form is solid. Bromine's reference form is Br2 liquid. You need two of bromines, right? Br2 we are referring to. Then write the solid ionic compound, magnesium bromide. Those two states are related by the formation enthalpy change. Then write the constituent gaseous signs of magnesium bromide. So Mg2 plus gas and 2 of Br minus gas. You have 2 Brs in the system, right? That constituent gaseous signs and the solid ionic lattice, the two states are related by lattice enthalpy. Right. Okay. Now, we need to convert these reference forms to these gaseous signs. For that, electron gain as well as ionizations are needed. For this one, first and second, both the ionizations are needed. To do the electron gains or the ionizations, first of all, you need to come up with the isolated gaseous atoms. Then only you can apply the electron gains and ionizations. So let's convert these things to isolated gaseous atoms, right? So magnesium can convert to magnesium gas, right? That can be done by applying the, just writing one thing is enough. Just writing one thing is enough. You can apply the sublimation here, or you can apply the atomization or fusion plus vaporization, no worries. So this thing will be there without a change, right? Then we can apply the ionizations now to convert this magnesium gas to magnesium 2 plus gas, right? So let's apply these ionizations, right? First convert that into plus 1 gas, delta H naught I1. Then let's convert that into plus 2 gas. Right? So another electron will be released. That electron and this electron, altogether 2 electrons. All of these states should be charge conserved as well as mass conserved. Mass conserved as well as charge conserved, right? So that 2 electrons are needed at this state, right? Right, no? Okay. Then forming the magnesium 2 plus gas is done. Now we need to convert this reference form of Br bromine to 2 of Br minus gas. So to apply the electron gain, first of all we need to come up with the isolated gaseous atoms. So first we need to convert this into isolated gaseous atoms, right? That can be done by the atomizations directly, because reference forms can be converted to gaseous atoms by atomization. or if you are thinking of applying bond dissociation, if you are thinking of applying bond dissociation to come up with isolated gaseous atoms, first you need to convert this thing into a gas, right? So to do the bond dissociation, right, you are supposed to break the bonds in a gaseous compound, right? Break the gaseous bonds, right? So let's go with that thing. අපි මේ විදිහට වැඩි කරමු. පොඩ්ඩක් යම්කිසි දෙයක් ඉගෙන ගන්න ඕන නිසා නේද? Let's go to the bond dissociation so that this can be converted to first gas by VAP, right? Vaporization. Or you can directly do the atomization, right? But I am trying to use the bond dissociation here to come up with the monoatomic gaseous forms. To come up with the bond dissociation, you definitely need to come up with the gaseous compounds. These will appear like they were, right? So now we can do the bond dissociation to come up with 2 of Br gas. So it's like this, no? It's like you are with some Br2 gas, no? So by breaking 1 mole of bonds, you will come up with 2 moles of Br gas atoms, right? This is in 1 mole of thing is enough. So always bond dissociation come up with the stoichiometric value here. Even here you can see the same stuff, right? Then make it atomization දාන්න බෑ හොඳේ. මේ change එකට ලියන්න එපා 2 of atomization කියලා. ඒක වැරදි. ඇයි වැරදි? මේ change එක ලියන්න බෑ 2 of atomization කියලා. Why it is false? So if it is to come up as atomization, you have to start with the reference form. මතකනේ atomization කියන්නේ. Atomization එක කරන්න start කරන reference form එක Br bromine ගේ reference form එක Br2 gas නෙමෙයි. So this conversion is not equal to 2 of atomization. මේක 2 of atomization equal වෙන්නේ නැහැ හොඳේ. ඔයාට මෙන්න මෙහෙම ගත්තා නම් මෙන්න මේක ගත්තා නම් 2 of atomization වල equal වෙනවා. Reference form convert into monoatomic gaseous form. මේක 2 of atomization. But not this, right? Atomization again reference form එක තමයි කන් මෙතන ප්‍රශ්නයක් වුණ නැහැ ඒක. මම මේ reference form එක තමයි Cl ගේ reference form එක Cl2 gas case. හරි. හරි. දැන් වැඩි ඉවර කරලා දාන්න තියෙන්නේ. Right? Now you have the monoatomic gaseous form now that you can come up with the electron gain to come up with this, right? So this delta H naught Eg. Here you clearly see you are supposed to produce 2 moles of Br minus. That means by applying just one electron gain, you will produce only 1 mole of Br minus. You need to produce such 2. So you need to multiply with 2. Right? So let's apply the Hayes law, Hayes relationship, right? So this is one route, this is the other route, right? This is the initial state, this is the final state. So this is one route to go from initial to final, this is the other route. Delta H naught F is equal to හරිද? ඔය තමයි කතාව. Done, right? Okay. ඔය තමයි magnesium bromide burn him cycle එක. ඉතින් ඔයාලා මේක use කරලා හරි ඕන enthalpy term එකක් හොයාගන්න පුළුවන් අනිත් enthalpy terms හැම එකකින් values දීලා තියෙනවා that is how we are supposed to draw the enthalpy Bornheim cycles actually Bornheim cycle is kind of a thermochemical cycle right thermochemical cycle එකක්ම තමයි ළමයි පොඩ්ඩක් ලොකු ටිකක් complex thermochemical cycle එකක්ම තමයි ඉතින් Bornheim cycle කියන්නේ right ne okay හරි නේද right so let's move to the next page number 10 දැන්ට ළමයි අපි මේ problem solving techniques දෙකක් ගැන කතා කරලා තියෙන්නේ හරි thermochemistry වල නැත්නම් enthalpy problem solving වල techniques දෙකක් ගැන කතා කරලා තියෙන්නේ first we had discussed about how to solve enthalpy problems with the use of equations and then we had discussed about how to solve these enthalpy problems with the use of thermochemical cycles. Even Bornheim cycle is a complex nature of thermochemical cycle. Then අපි කතා කරන්නේ තුන්වෙනි ක්‍රමයට. Now we are going towards the third form of solving right enthalpy questions. Problem solving the third method. That is referred to as the enthalpy diagram. Enthalpy diagram. Or enthalpy diagram එකක් use කරලා කොහොමද බලමු එහෙනම්. අපි solve කරන්න. How to use the enthalpy diagram in problem solving. That is what we are going to discuss now. Right? Normally enthalpy diagram situation appears with these kind of questions related to Bornheim cycles. Bornheim cycles වලට දෙන data relate කළාම තමයි සාමාන්‍ය enthalpy diagrams අදින්න කියලා questions වල එන්නේ. හරි? අපි බලමු මොකක්ද කරන්න තියෙන්නේ. හරි ලේසි වැඩක් ළමයි. When it comes to enthalpy diagram, right? So actually it is also like a Bornheim cycle. So if you are supposed to draw the enthalpy diagram of NaCl, if they have asked you to draw the enthalpy diagram of NaCl, actually what you need to do is just draw the Bornheim cycle. Just draw the Bornheim cycle and come up with some enthalpy axis. That's all, right? What are we energy diagram එක අදින්න කිව්වනම් ඔයාට මේක energy diagram එක enthalpy diagram එක අදින්න කිව්වනම් NaCl ගේ ඔයාට ගන්න තිය සරල දෙයක් මොකද්ද Bornheim cycle එක කොහොමද අදින්න ඇඳලා මේ පැත්තෙන් enthalpy axis mark කරන්න. කියන්නේ enthalpy kilojoules නැත්නම් kilojoules mole කියලා. ඔච්චර කරන් තියෙන්නේ. and 0 mark කරන්න. reference form එකෙන් 0 mark කරන්න. reference form එකෙන් 0 mark කරන්න. හරි එච්චරයි. දැන් ඉතින් වාගේ enthalpy diagram එක හරි. This is your enthalpy diagram. Right? Very simple stuff. Just draw as a Bornheim cycle and mark the right energy axis. මේකත් ඔයාට energy diagram කරන්න ඕන, enthalpy diagram කරන්න ඕන. හරි? චර තමයි කරන් තියෙන්නේ. enthalpy axis එක දාන්න ඉච්චරයි. Right? The thing is done. And mark the 0 as the reference form. We know the enthalpy of the reference form is 0. formation enthalpy right. හරි වැඩේ ඉවරයි. හරි සිම්පල් ඉතින් නා. පුංචි කාරණා ටිකක් කියන්න තියෙනවා. ඔච්චර තමයි සරලව ගියොත් ඔක තමයි කරන් තියෙන්නේ. හරි. තව පොඩක් දේවල් ටික කතා කරමු මේක සම්බන්ධයෙන්. හරි. When it comes to enthalpy diagram, right? These up arrows and down arrows are with some meaning. හරිද? දැන් බෝන් හිම සයිකල් එකක් වගේ නෙමෙයි. enthalpy diagram එකක් ගත්තාම දෙකේ තියෙන වෙනස්කම් පොඩක් කතා කරොත් පළවෙනි වෙනස්කම තමයි you have to have a axis, enthalpy axis with the enthalpy diagram, not with the bone hill cycle. දැන් පළවෙනි වෙනස්කම, first difference. ඊට පස්සේ වැදගත්ම වෙනස තමයි ඊට පස්සේ when you are with a enthalpy axis like this with the enthalpy diagram, these arrows, I mean whether it is upwards or downwards, that is with a meaning, right? Upward දෙනවා කියලා කියන්නේ enthalpy එක වැඩි වෙනවා කියන එක. Downward කියන්නේ enthalpy එක අඩු වෙනවා කියන. Increasement of enthalpy means delta H is positive. Decreasement of enthalpy means delta H is negative. So all the exothermic or the negative delta H values should be marked as downward arrows when you are with the enthalpy axis like this. All the positive enthalpy changes, the endothermic enthalpy changes should be marked as up arrows. Right? That is the normal idea. Right? That is what happens when you are assigning an axis as enthalpy in the enthalpy diagram. Hurry? Now bone hair cycle එකේ එහෙම කතාවක් නැහැ ඉතින්. bone hair cycle එකේ up arrow එකකින් මේ endothermic ම වෙන්න ඕනේ, down arrow එකකින් exothermic වෙන්න ඕනේ කියලා කතාවක් bone hair cycle එකේ නැහැ. නේ? අපි නිකන් thermochemical cycle එකක් ගහනකොට එහෙම arrow එකේ direction එකකින් කියන්නේ නැහැ නේ positive negative කියලා. හරි? But when it comes to right enthalpy diagrams, yes, whether it is upwards or downwards, that is with a meaning. So if you are with endothermic enthalpy changes, delta H positive things, you have to mark them as upward arrows. If you are dealing with exothermic enthalpy changes, negative delta H naught values, those should be marked as downward arrows. උච්චර තමයි ඉතින් දැනගන්න තියෙන්නේ. නැත්තම් සරලව කිව්වොත් enthalpy diagram එකයි energy මේ bone hair cycle එක වගේ තමයි. Just the difference of enthalpy axis appearing there. හරි? අර බින්දුව දැම්මොත් මෙතනින් බින්දුවට වඩා වැඩි යොමු වෙයි. මේ අඩු වෙනවා. හරි? so මේකලුත් ඔයාලට තේරෙන්නේ නැති. Normally when we considering stable compounds, their delta H naught F values are negative. හරි? stable compounds consider කරද්දී සාමාන්‍යයෙන් ඒගොල්ලෝ delta H naught F values negative values තමයි එන්නේ. ඉතින් මේ diagram එකලුත් ඒක පේනවා. හරි? හැමතිස්සෙම delta H naught F negative කියලා අපි කියන්නේ නැහැ. But for the stable compounds appearing in the nature, in nature කියන සාමාන්‍ය nature in stable compound ඒ වගේ දේවල්දී delta H naught F value එක negative value එකක් තමයි දෙන්නේ. right? හරි? පැහැදිලි? right. එහෙනම් අපි මට එහෙනම් ඇඳලා දෙන්න ඕගොල්ලෝ අර එහා පැත්තේ තියෙන ඇලුමිනියම් ක්ලෝරයිඩ් කතාව ළමයි මේ අනිත් එක මේ දැන් මෙතනදී ඔයාලට පේනවා මේ උඩට ලියපු හැම එකම පොසිටිව් වේ හොඳේ පේනව නේද මේ fusion, vaporization, atomization, sublimation all involving in breaking bonds or weakening bonds නේද fusion කියලා කියන්නේ solid එකක් liquid කරනවා weakening of bonds particles add කරනවා vaporization කියන්නේ liquid එක gas කරනවා weakening of bonds atomization means you are converting the solid to gaseous atoms. That means all the bonds in the solid will be broken, breaking of bonds. Sublimation is same. Hurry, again breaking bonds, endothermic. Make breaking here, also some bond is broken between the electron and the positively charged nucleus. අර nucleus එකයි ඔයාගේ valence shell electron එක අතර තියෙන bond එක තමයි break වෙන්නේ. electron එක ගැලවිලා යද්දි එයා අර nucleus එකේ තිබෙන electrostatic attraction එක තමයි break වෙන්නේ. හරි. ඒකට bond breaking endothermic needed to absorb heat. Here as well bond breaking endothermic. මේක when it comes to electron gains, only 3 atoms are with endothermic electron gains: beryllium, magnesium and nitrogen. All the other atoms are with exothermic electron gains. First electron gain එක endothermic වෙන්නේ beryllium, magnesium, nitrogen විතරයි. අනිත් හැම එකේම first electron gain එක exothermic. ඒක තමයි මේ පහළට exothermic. delta H negative. හරි. electron gains පහළට එන්නේ ඒකයි. That is this is what? This is what? Lattice formation. That is formation. Na? That is formation means, right? Forming bonds. Forming bonds. That means exothermic. That is why the arrow is downwards. Right now, when coming up with enthalpy diagrams, upward arrows indicate endothermic, that is positive enthalpy changes. Downward arrows indicate exothermic, that is not negative enthalpy changes. Right now, මේකෙත් ඔය කතාවට ගිහින්ම දිනවා. හරි? Right. අපි එනම් අන්තිමුද ඇලුමිනියම් ක්ලෝරයිඩ් enthalpy diagram එක. enthalpy diagram එකක් අඳලා ඇලුමිනියම් ක්ලෝරයිඩ් problem solve කරමු, which is appearing at page number 10. ළමයි, if the values are given like this in a question, if the values are given like this, you are supposed to write those values here instead of the symbols. Symbols දාන්න එපා. values දීලා තියෙනවා නම් කෙලින්ම values ටික මෙතන ලියන් යන්න. හරිද? values දීලා නැත්නම් තමයි symbols දාන්න. හරිද? එතකොට දැන් මේකේදී ඔයා දැන් මේ question එක කරද්දි කෙලින්ම values ටික මෙතන ලියන් යන්න. ඊට පස්සේ values ටික මෙහෙම ලිව්වා, relationship එක උත්තරේ ගත්තා. Right? Just do the stuff. Just do the problem appearing in page number 10. The enthalpy diagram. We need an enthalpy diagram there, right? Not the bond heat cycle, enthalpy diagram. You need to mark the enthalpy axis as well, as we are looking for enthalpy diagram. reference form එකද හැම metal එකකම reference form එකෙන් solid එක other than mercury විතරයි liquid එකක් විදිහට ඉන්නේ අනිත් හැම එකම monoatomic solid form එකේ තියෙන reference form එක metals right බලමු let's try to draw the enthalpy diagram for what aluminium chloride in this question, right? Positive enthalpy changes upwards arrows වලින් යන්න ඕනේ up arrows වලින් negative enthalpy changes down arrows වලින් එන්න ඕනේ හරි ඒක නිසා සාමාන්‍යයෙන් අර අපි කියනවා මේ පිළිවෙලට වැඩි කරන්න තොරට ලීසි මුලින්ම කැටයන් එකේ වැඩ ටික ඉවර කරලා ඇනයන් එකේ වැඩ වලට වහින්න සාමාන්‍ය හිතයි ක්‍රමය හරි මුලින්ම කැටයන් එක right gaseous sign එක කරලා ඉවරලා තමයි ඇනයන් එකේ වැඩ වලට වහින්නේ පිළිවෙලට යන්න right this is about the enthalpy diagrams right so the system is ACSD right so first you need to come up with the enthalpy axis start with the reference form one aluminium atom and the chlorine's reference form is Cl2 gas you need such 3 chlorines that means 3 by 2 right there's a zero form right then this thing solid ionic compound or solid ionic lattice this value is given as the formation enthalpy is given as minus 437 right අර මේ පැත්ත x කිලෝ ජූස් කියලා දාලා තියෙන නිසා මේක අවශ්‍යමත් නැහැ. ඔහොම දැම්මත් ලකුණු දෙනවා. හරි. මෙතන x කිලෝ ජූස් කියලා දාලා තියෙනවා. හරි. මේක enthalpy diagram එකක්. හරි. එතකොට මේකේ energy axis එකක් තියෙනවා. ඔය units දාලා යන්න ඕනේ නැහැ. unit එක විතර represent වෙනවා. හරිද? දැන් අරවල units දාන්න ඕනේ. දැන් බෝන් නිබ සයිකල් කියලා නම් ක්වෙස්චන් එක ඇවිල්ලා තියෙන්නේ බෝන් නිබ සයිකල් එකේ මෙහෙම ඇක්සිස් එක නැති නිසා මේ හැම ඇරෝ එකක් එක්ක යුනිට්ස් දාන්න ඕනේ බෝන් නිබ සයිකල් නම් හරි පරිස්සමෙන් ඒක තේරුම් ගන්න අදහස තේරුම් ගන්න බෝන් නිබ සයිකල් නම් ඔයාගේ එන්තැල්පි ඇක්සිස් එකක් නැති නිසා මේ හැම ඇරෝ එකක්ම යුනිට් එක දාන්න ඕනේ දැන් මේකේ ඇක්සිස් එකක් තියෙනවනේ කිලෝ ජූස් කියලා මාක් කරලා යුනිට් එක දාන්න ඕනේ කිලෝ ජූස් කියලා රිප්‍රසන්ට් වෙනවා aluminium 3 plus gaseous science no very well you know that that is enthalpy that is what they are asking no this is what they are asking right then to convert the aluminium into gaseous form they have given a sublimation enthalpy yes provide the sublimation enthalpy. That is given as plus 326. Right? Okay. Then aluminium grade ඉවර කරලා මුලින් නේ කවන්නද ලේසි. Right? aluminium grade ඉවර කරලා මු. Aluminium first ionization, second and third ionizations are given. That is plus 577. Second ionization. Another electron is released. Plus 1820. Third ionization. $2,740. Right. Then bond dissociation is given to convert the Cl gas to monoatomic gaseous form. So with that you will form 3 of Cl gases. So bond dissociation should be done 1.5 times. 1.5 times of bonds should be broken, right? Bonds 1.5 dinner. So the value is 244 plus 244 into 1.5. Right? 1.5 bonds should be broken, right? Now, electron gain 3 times should be done. Minus 349 into 3, as 3 Cl minus ions are needed. Alright. Now let's come up with the Hayes law to find the answer. So applying Hayes law. Right? මේලා kilojoules per mole කියලා දාන්න කවන්නේ. mole කියලා දාන්න. better. kilojoules කිව්ව කවන්නේ kilojoules mole is better. Right? Okay, එතකොට අපි ලියමු. So this is one root. එතකොට unit එකත් එක ලියන්න. unit එකත් ලියන්න. reheap ලියද්දි. This is the other pathway. So 326 plus 577 plus 1820 plus 2740 plus 3 by 2 into 244, right, minus 3 into right. Right now, kilojoules mole plus delta H naught tail. you can simplify this stuff and come up with the answer. It will be given in kilojoules per mole, right? බලමු simplify කරලා නේද? කොහොමද වෙන්නේ කියලා. Right? Here subject that thing, no? So these things become as minus, that is right. Minus එයාට 5219 කියන්නේ කොහොම වැලියක් එන්න ඕනි. ඒක මයිනස් වැලියක් වෙන්න ඕනේ හරි. ඩවුන්වර්ඩ් තියෙන්නේ. arrow එක. හරි. ඩවුන්වර්ඩ් න arrow එක තියෙන්නේ මයිනස් වෙන්න ඕනේ. හරි. ඊළඟ තමයි enthalpy diagram එකකින් problem solving එකක් කරන්න. Right? The thing is clear. That is the third form. That is the third technique available to do the problem solving. Right? Problem solving වලට available third technique තමයි කතා කරන්නේ. shape නේ. හරි. Right. Okay. අපි ළඟ ඊට පස්සේ යමු ළමයි මේ fourth problem solving method එකට. හරි? හතරවෙනි problem solving method එකට යමු. ඒකට ගිහිල්ලා ඊටු interval ටික කතා කරලා දාමු ඩක් ගාලා. හරි? Let's move towards the fourth problem solving technique. Right, this is known as the algebraic method, which is appearing at page number 11. The algebraic method. Right, let's try to use the algebraic method in problem solving. Right, this is at the page number 11. Make out there, we are going right. Page number 11. You have the algebraic method. So this is known as a MCQ technique. Right, algebraic method is known as a MCQ technique. Right, let's try to use that technique to solve questions, right? හරි. එහෙනම් අපි මේ විදිහට යමු. මම හිතනවා enthalpy diagram එක ගැන යම් අවබෝධයක් ඉන්නද කියලා මේ වැඩේදී. හරි. ඉතින් අර බෝන් cycle එකම වගේ තමයි. with the energy axis. energy axis එක තියෙනකොට ඔයා unit එක ලියලා යන්න ඕනේ නැහැ හොදටම. axis එකේ unit එක represent වෙන්න නිසා. right? හරි. එහෙනම් අපි move වෙන page number 11 වලට. There are major problem solving techniques හතරයි තියෙන්නේ. enthalpy diagram එක third technique එක. දැන් අපි යන්නේ හතරවෙනි කතාවට. ඉතින් හතරවෙනි කතාව කියන්නේ මොකක්ද MCQ technique එක. This is normally used to right do the problem solving in MCQs, right? හරි බලමු. Fourth technique. Right, known as algebraic method, right? So number 4, right, algebraic method. MCQ technique. Of problem solving. Right. Let's come up with the algebraic method. හරි. මුලින්ම ළමයි මම මේ question එක ලියා ගන්නම්, right? ඊට පස්සේ අපි බලමු කොහොමද algebraic method එක මේකට use කරන්නේ කියලා. හරි. ඒතර data විදිහට දීලා තියෙනවා. first example එකේ data විදිහට තියෙනවා මෙහෙම නේද? 2 of Fe solid plus O2 gas. Give me 2 of FeO solid. මේ equations ටික දීලා තියෙනවා. Right, Fe3O4. ඔය data ටික වල දීලා තියෙනවා. Delta H naught values of these reactions are also given. Minus 544. Right, and what they are asking is the enthalpy change of this thing. හරි මේක වැලියු තමයි අහන්නේ. හරි බලමු මේ වගේ MCQ එකට කොහොමද MCQ ටෙක්නික් එක algebraic method use කරන්න කියලා. හරි. So first we'll consider this one as the equation 1, this one as the equation 2, this one as the equation 3, and let's take this one as the equation 4. Right, now we need to come up with the algebraic relationship between these 4 equations. ඒ අතර තියෙන algebraic relationship එක අපි build up කරගන්න ඕනේ. හරි. ඇත්තටම ළමයි chemical reaction එකක් කියන්නේ if you are regarding a chemical reaction, actually those are all about mass balances. chemical equation එකක් කියන්නේ සරලව ගියොත් mass balance එකක් තමයි නේද? ඒ කියන්නේ සරලව මේ chemical equation එක අපිට මෙහෙම අර row එක නේද සමානයි කියලා දාලා ලියන්න පුළුවන්. This side is equal to this side. This side is equal to this side. This side is equal to this side. සමාන ලකුණු දාලා ගන්න ඕනේ. right, mass balance එකක් විදියට. හරි. ඒක තමයි එතන use කරන්න යන්නේ. ඒක තමයි algebraic relationship එක විදියට use කරන්න යන්නේ. equalities, right? algebraic operations වලට. හරිද? හරි. මෙහෙම වැඩි කරන්න. හරි මේ ටෙක්නික් එකෙන් මෙහෙම වැඩක් කරන්නේ. හරි. මුලින්ම අපි කරන්නේ we have the equation number 4, right? The equation which we need to come up with the delta H naught value. Right? First, what we do is, yeah, it's like this. So let's think of this one. In this one, in this equation, the equation we need to come up with the delta H naught R, right? We have one of FeO at the left hand side, one of Fe2O3 at the left hand side, and one of Fe3O4 at the right hand side, right? So what we need to do here is, actually we need to, right, first we need to find out some chemical species to represent these 3 equations. We need to come up with some right suitable chemical components appearing in this equation to represent these three equations. හරි මේ equation තුන represent කරන්න මෙතනින් අපිට chemical components ලව තෝරගන්න වෙනවා. දැන් මුලින්ම කරන වැඩි. හරි. So එතකොට if you are thinking of FeO, right? FeO, that FeO is appearing only with the first equation. So ළමයි සාම අපි තෝරගනිද්දී අනිවාර්යෙන් ඒ equation එක represent කරන්න chemical species කෙනෙක් තෝරගනිද්දී හරි එයා එක equation එක විතරයි ඉන්න පුළුවන්. දැන් FeO කියන එක්කෙනා ඉන්නේ first equation එකේ විතරයි. එහෙනම් we can use the FeO to represent the first equation. හරි ඒ වගේ check කරන කට්ටිය Fe2O3 කියන එක ඉන්නේ එක equation එකක විතරද? ඔව් Fe2O3 කියන එක ඉන්නේ මෙතන second equation එකේ විතරයි. So Fe2O3 can be used to represent the second equation. හරි ඔන්න ඔක තමයි මුලින්ම කරන්න ඕන වැඩේ. හරි මෙතන තියෙන chemical components ලගෙන් මේ equation represent කරන කට්ටියව තෝරගන්න තමයි මුලින්ම කරන්න ඕනේ. ඒක කරද්දී අනිවාර්යයෙන්ම ඒ chemical component අදාළ equation එක represent කරන්න suitable වෙන්නේ only if right that chemical component is appearing only with that equation, only with that reaction. එතකොට Fe3O4 ගත්තොත් Fe3O4 ඉන්නේ the Fe3O4 appears only with the third reaction. So Fe3O4 is suitable to represent the third reaction, right? That is the first thing to do, right? Selecting the suitable chemical components in your equation to represent the right equations here, right? For that kind of a chemical component will be suitable only if right that chemical component is appearing with that right selected reaction only, right? හරියම මෙහෙම කරන් දින වැඩි හරි ලේසි දැන් වැඩි. So then now we are writing the algebraic operation here. The 4 is equal to, this is the algebraic operation, the most important stuff here. 4 is equal to so number 1 FeO. We need one FeO molecule at the left hand side. Your FeO is appearing at the right hand side, right? And 2 of those are appearing. First we need to bring that thing to left hand side. Meow left again. That means we have to no need to take the 1, but we need to take the minus 1. But minus 1 තමයි තේරු ගන්න වෙන්නේ වැඩේට. Right? Because we need to bring this FeO to left hand side because we need the FeO at the left hand side, right? So 1 හරියන්නේ minus 1 ගත්තම සමාන ලකුණු කතාපතකයි මෙයා මාරු පැත්ත මාරු minus 1 කියන ළම ඇත්තටම reaction එක අර ඔයගේ side එක මාරු වෙනවා කියන එක. Right? Okay. So minus 1. හැබැයි minus 1 වලින් මට එනවා 2 of FeO. But we need this 1 of FeO. So that we need to divide that thing by 2 as well. So මෙයා දෙකිනුත් බෙදන්න ඕනේ. මෙයා දෙකින් බෙදුවා තමයි මෙයාගේ නේද? දෙකින් බෙදුවා තමයි 1 FeO වෙන්නේ. දෙකින් බෙදන්න ඕනේ. හරි නේද? හරි. දැන් එහෙනම් මෙයාගේ වැඩ ටික ඉවරයි. හරි. Fe2O3. I need the Fe2O3, 1 mole of Fe2O3 at the left hand side. In our equation, 1 mole of Fe2O3 is appearing at the left hand side. So where is the Fe2O3? This is the Fe2O3. It is appearing at the left hand side. So you have to bring this thing to this side, to the other side. That means minus 2 should be right considered. Minus 2 then consider. හරි හැබැයි මට ඕනේ එක මෝල් එකනේ එකයි ඕනේ දෙකකින් බෙදන්නත් ඕනේ හරි right we need Fe3O4 at the right hand side but Fe3O4 is available at the left hand side in this case, so we have to bring this thing to the other side. We need just 1 and 1 is only appearing. Now මෙයා එහා පැත්තට ගෙනාවම විතරක් ඇති. So minus 3. Right? This is the algebraic operation. දැන් මේක ලියද්දි හරි මේ පිළිවෙල ලියම අන්ලියු විදිහටම ලියන්න හොඳේ. දැන් මෙතන ඔයාලට පේනවා ඇති round කරපු numbers තියෙනවා. මේ circle කරපු numbers තියෙනවා, නිකන් numbers තියෙනවා. මේ සර්කල් කරනවා නම් සර්කල් කරලම දාන්න හොඳේ. අර සර්කල් කරලා තියෙන්නේ මේ ඉක්වේෂන්ස් විතර. නැත්නම් ඇල්ජිබ්‍රික් ඔපරේෂන් එකයි ඉක්වේෂන් නම්බර් එකයි පැටලෙනවා. හරි. ඉක්වේෂන්ස් අපි නම්බර් කරලා තියෙන්නේ රවුන්ඩ් කරලා. ඔයාට ඔය පැටලෙනවා නේ ABC කියලා දාගන්න. මොකද සාමාන්‍ය D වෙන්නේ හරි සාමාන්‍ය වැලියුස් දෙන්නේ ඩෙල්ටා H 1 2 3 කියලා උඩ පැටලෙනවා. හරි. ඒක නිසා ABC දාන්න එපා. හරි. 1 2 3 දානකොට හොඳයි වැඩි යන්නේ. ඇල්ජිබ්‍රික් ඔපරේෂන් කරලා දාලා ඒක හොඳයි. නැති වැඩි කරා. see. So what we need to do, so take the minus 1 divided by 2. So minus 1. So the 1 එකේ minus. So 544 එකේ minus is plus 544 divided by 2. හරි ඊපස්සේ minus 2. minus 2 නේ. මේක plus වෙනවා ආයෙත්. minus minus plus වෙනවා. ඊට පස්සේ මේක just minus 3. So this is the answer. One answer. This is delta H. What only R නගේ R කියලා දාගන්න. අපි කොහොමද? Let's consider this as delta R. Right? So you can simplify and come up with the answer now. Right? Are lazy. අර මේකේ ට්‍රික් එක තියෙන්නේ මේ මෙන්න මෙතන මේ මැතමැටිකල් ඔපරේෂන් එකත් එක්ක මේ ඇල්ජිබ්‍රික් ඔපරේෂන් එක තමයි කතාව. මේක ලියාගන්න තමයි වැඩි. So do the simplification. Right. minus 24 kilo. This is very easy method. It's very easy. Using the algebraic relationship is very easy to solve these questions. Right now. Gilang question තනියම කරන්න. Just solve the next one. Solve the next one. තනියම කරන්න. වෙලා ඉන්නේ. they are asking the delta H naught R of this. Just build out the algebraic operation. No question එකක් පොඩ්ඩක් හොඳ question එකක් හරි. ඉතින් මම තෝරගත්ත questions ටික පොඩ්ඩක් අර නෙන hard වෙන විදිහට තෝරගත්තා. ඔයාලට අලුත් දෙයක් කියලා දෙන්නත් එක්ක. algebraic operation set කරගත්තා හරි. සුළු කරන එක සාමාන්‍ය දෙයක්. right බලමු ළමයි. මොකද කරන්න පුළුවන් කියලා මේකට. See, this is how we are supposed to come up with this algebraic relationship, right? හරි. Let's take this one as 1. This as 2. This as 3. And this as 4. Well, මේ represent කරන මුලින්ම කට්ටිය තෝර ගන්න ඕන. NO gas. NO gas is appearing only at the third D equation. Hurry. O gas. O gas appearing at only at the second D equation. Hurry. Then NO2 gas. NO2 gas is only appearing at the third D equation, but to represent the third D equation, we had found someone, right? Before. Calling it හොයාගෙන තියෙන්නේ. තුන්වෙනි එක represent කරන මෙයාගේ වැඩක් නැහැ ඇති. අර මෙයාගේ වැඩක් නැහැ ඇති. හරිද? මොකද third D equation represent කරන එක තෝරගෙන ඉවරයි. දැන් ඉතින් මොකද එයා ඉන්නේ මෙතන විතරයි කියලා එයාගේ වැඩක් නැහැ. third D equation represent කරන්න දෙයක් නැහැ නේ. තෝරගෙන ඉවරයි. අර කියන්නේ අපායට යනවවත් නේද කලින් යන්න ඕනි කියලා. ඒක තමයි. ඒ නම් මුලින්ම මේක කරලා තෝරගන්න හරි. හරි. තෝරාලා බලනවා මේ second first equation එක represent කරන කවුරුත් නැහැ. නේ ප්‍රශ්නයක් බය වෙන්න එපා. හරි බලමු මේක solve කරගන්න කොහොමද කියලා. හරි මුලින් මේ දෙන්න වැඩි ඉවරයක් කරලා ඉමු. ඊට පස්සේ first එක ගැන හිතන්න පුළුවන්. right හරි. So we can say take the algebraic form 4 is equal to we need one of NO gas at the left hand side. Yes, one is appearing at the left hand side. We can use the third one directly. Correct. So one of oxygen gas is seated at the left hand side, but that is appearing at the right hand side here. So we have to bring this thing to this one, and we have to divide it by 2 නේ. දෙක වැඩ කරන දෙකෙන් බෙදන්න බෑ. ඒතකොට 1 වෙන්නේ. නම් මොකද වෙන්නේ? සත්‍යේ. So 2 minus 2 has to be taken. Minus 2 has to be taken because we need to be come to this side. Left again has to be divided by 2. හරි. හරි. එතකොට මේ දෙන්න හැන්ඩල් කරලා ඉවරයි. හරිද? 1 හැන්ඩල් කරන්න ඕනේ. දැන් කොහොමද 1 යූස් කරන්න වැඩියට? මෙහෙමයි ළමයි. දැන් බලන්න දැන් මේ ඉක්වේෂන් දෙක කන්සිඩර් කරලා පස්සේ මේ විදිහට අනිවාර්යෙන් මේකේ දැන්ට නැති කට්ටිය සෙට් වෙලා දින වැඩේට. හරි මම උදාහරණයක් ගන්න ඕන. දැන් මේ ඉක්වේෂන් එකේ O3 ගෑස් නැහැනේ. මේ ඉක්වේෂන් එකේ O3 ගෑස් නැහැ. අය මේ දෙක කරාට පස්සේ වාට O3 ගෑස් අනිවාර්යෙන් ඇවිල්ලා තියෙන දැන්. මේ දෙක යූස් කරනකොට ඉක්වේෂන් 3 යූස් කරනකොට O3 ගෑස් ඇවිල්ලා දින වැඩේට. මෙතන නෑ හැබැයි. දැන් මේ ඉක්වේෂන් යූස් කරද්දී වාට O2 ගෑස් වැඩි ඉන්නෝල් වෙනවා. මේක යූස් කරද්දී. O2 ගෑස් ගේ half එක දැන් මෙතන මේ පැත්තට ඇවිල්ලා තියෙන්නේ. හරිද? දැන් මේකේ නෑ. ඔය අනවශ්‍ය ආපු කට්ටිය කපා ගන්න අයින් කරන්න තමයි ඉක්වේෂන් 1 එක අපි යූස් කරන්නේ. හරිද? සරලව කිව්වොත් දැන් මේ වැඩේදී O3 ගෑස් කෙනෙක් කියලා මේ වැඩේදී O2 ගෑස් කෙනෙක් දැන් වැඩේට ඉන්නෝල්ලා තියෙන මෙතනට ඇවිල්ලා තියෙන්නේ දැන් අනවශ්‍ය දෙන්නේ. ඔය දෙන්නව කපා ගන්න තමයි මේක යූස් කරන්නේ. හරිද? දැන් හරිය පුළුවන් කරමු. හරි. දෙන්නෙක් කපන්න යන්න එපා. එක එක කපුවම ඇති. දෙන්නෙක් පයින් කරන්න දෙන්නෙක් ඇවිල්ලා දිනවා හරි කරදරයි. හැබැයි එක්කෙනෙක් පයින් කරගන්න මේක යූස් කරාම ඇති. හරි? අනිත් එක නිකම් අයින් වෙනවා ඒක. කොහොමද මෙයා රිප්‍රසන්ට් කරගන්න ඕනේ මේක ඇස්සේ? හරිද? එන එක යූස් කරමු. බලමු මොකක්ද යූස් කරන්නේ. දැන් O2 ගෑස් මේ දෙකේම අපිය වෙනවනේ. කරදරයිනේ O2 ගෑස් එක වැඩ කරන එක. O2 ගෑස් දෙකේම අපිය කරදරයි ඒක. හරි? එක්කෙනෙක් විතරක් අපිය එක්කෙනෙක් තෝරගන්න. O3 ගෑස්. එතන මේ ඉක්වේෂන් නැති හරි මේගොල්ලගේ තිබ්බ කට්ටිය දැන් වැඩේ සෙට් වෙලා තියෙන්නේ. ඒගොල්ලෝ එක එක විතරක් අපිය වෙන එක තෝරලා ලේසි වැඩේ ඉවරක් කරගන්න. හරි? right O3 ගෑස්. එහෙනම් O3 ගෑස් තමයි කනෙක්ට් කරන්නේ. හරි? දැන් හොඳට මේක උඩ ගන්න. ඔයාගේ third equation direct use කරනකොට O3 ගෑස් කෙන් දැන් වැඩිපුර මේ පැත්තට ඇවිල්ලා තියෙන්නේ. එයා ඉන්න හොඳ නැහැ. අයින් කරගන්න ඕනේ. ඒක අකුණු අයින් කරන්න පුළුවන්. මේක මෙහෙට ගෙනිච්චා. දෙකෙන් බෙදුවා. මේක දෙකෙන් බෙදපු ගමන් කෙලින්ම මේක කැපිලා යනවා. මෙයා මෙහෙට ගෙනිච්ච ගමන් O3 ගෑස් කෙනේ මේ පැත්තට එනවා. ඒ O3 ගෑස්ට මේ පැත්තේ ඉන්න O3 ගෑස් කැපෙනවා. හරි? ඔළුවෙන් හදන්න ඕනේ. ආයෙත් වෙන වෙන ලියලි හදන්න බෑ. මේ MCQ ගන්න. MCQ හදන්න කොළවල ලියලි ඉන්නේ. හරිද? මේ O3 ගෑස් අයින් කරගන්න මොකද කරන්නේ? අනිවාර්යෙන් O3 ගෑස් එක එහා පැත්තට එන්න. මේක ඩිරෙක්ට් යූස් වෙලා තියෙන්නේ. ප්ලස් විදිහට. O3 ගෑස් මේ පැත්තට එන්න ඕනේ. කියන්නේ ෆස්ට් ඉක්වේෂන් එකේ මයිනස් ගන්න වෙනවා. ඒකේ එක O3 ගෑස් කෙනෙක් විතරයි මේකෙන් ආවේ මේ පැත්තට. එහෙනම් එක O3 ගෑස් කෙනෙක් වෙන්නේ දෙකෙන් බෙදන්න. හරි? නොහොම තමයි ෆස්ට් ඉක්වේෂන් එක. හරි? ෂිෆ්ට් හරි. ඕන නිකන් කරලා බලන්න අනිවාර්යෙන් ඔය කරන වැඩේ ඇස්සේ O2 ල කැපිලා යනවා. ගෙදර ගිහලා හරි බලලා බලන්න. අනිවාර්යෙන් O2 කැපෙනවා. දැන් O2 මෙහෙට එන්නේ. O2 මෙහෙට එනවා 3O2 වෙනවා. කැපෙනවා ෂුවර්. කැපෙනවා තමයි ඉන්නේ. DT යූස් කරලා බලන්න. O2 කැපෙනවා. එක්කෙනෙක් විතර කරාම ඇති වෙනවා. So let's come up with the thing then. Delta H naught R then is equal to 3 means minus 427 to was say minus 2 divided by 2 that means minus 3 කියන්නේ මේකනේ minus 1 maintain minus 2 ගත්තම 495 එක minus වෙනවා. right ඊට පස්සේ minus 1 minus අරවන plus වෙනවා. ඉතින් ඔහොම ලස්සනට ආන්සර් කියනවා. minus 233 කියලා එනවා. හරිද? right okay තව ඒ වගේ ක්වෙස්චන් එකක් වඩ දිනවා තනියම ඉදදී හදන්න right ඒක තනියම හදන්න right ඉතින් ඔය knowledge එකකින් වඩ කරගන්න පුළුවන් ඒක හරි ඒකෙත් මේ වගේ වැඩක් කරන්න වෙයි ගොක් වෙලාවට මට විදියට මොකද HNO2 can be used to represent the fourth equation NCl solid can be used to represent third equation HCl gas can be used to yeah still the third equation එකෙන් වැඩක් නැහැ නේ Na2 solid කියන එක use කරන්න පුළුවන් to represent the yeah first equation එතකොට HNO2 liquid කින් fourth එක represent වෙනවා NaCl solid කියන එක නාගේ second එක represent වෙනවා NaNO2 කියන එක නාගේ first එක represent වෙනවා second equation එක represent කරන්න කෙනෙක් නැති වෙයි ඔයාට. ඒකට මේ වගේ වැඩක් කරන්න වෙයි. right? ඉතින් ඔක් කළා ලස්සනට ගාන හදලා ගන්න. right? කියලා දෙක කරන්න. හරි? ඉතින් ඕක තමයි algebra method එක. ඉතින් ඕක අපි use කරනවා MCQ problem solving වලට. හරි? right. අපිට අක් ගාලා ළමයි මේ පොඩ්ඩක් කතා කරමු ඔයගොල්ලෝගේ ඉතුරු enthalpy terms ටික ගැන. අපිට මේ enthalpy terms ටික ඉවරලා අපිට break එකක් ගන්න පුළුවන්. ඊට පස්සේ ඊළඟ session එකේදී අපි යනවා entropy and delta G වල පැත්තට. හරි? right. අපි එහෙනම් යමු ඊට පස්සේ වාගේ 11th enthalpy term එක ගැන කතා කරමු. හරි නිකන් පොඩි enthalpy term වැඩි equations හදන්න පැත්තක් නෙමෙයි ළමයි. වැඩි equations හදන්න ටිකක් නෙමෙයි දැන් තියෙන්නේ. හරි නමුත් අපි enthalpy terms ටික ඔක්කොම කතා කරන්න ඕන නිසා ඒ ටික මතක් කරගමු. right? enthalpy terms අපි 10ක් දැන්ට complete කරලා දිනවා. problem solving techniques හතරම කතා කරලා දිනවා. හරි? නමුත් අර just to complete the stuff, right? We'll discuss about the other enthalpy terms as well. ඔකේ අන්තිම enthalpy term පොඩ්ඩක් වැදගත්. delta H not R again. Let's quickly go to the stuff appearing there. Nothing much to write there, right? Okay. Right. හරි එහෙනම් අපි යමු දායිසරයක්. අපි යමු 11th එකට. right? 11th enthalpy term. Standard hydration enthalpy, right? 11th. Standard enthalpy change of hydration. Oh, hydration enthalpy. මේකින් ළමයි මේ පැත්තෙන් ගත්තොත් සාමාන්‍යයෙන් questions අහිනු ඔක්කොලාට MCQ ගේ side එක වගේ නේ statements වගේ හැදෙන්න පුළුවන්. First of all, what this means? Hydration enthalpy, right? Hydration enthalpy. Right, that means, right? You are supposed to convert gaseous ions. This is simple meaning. You're supposed to convert the gaseous ions to gaseous aqueous ions. To aqueous ions. That's it, right? You are supposed to convert the gaseous ions to aqueous ions. Just the change in physical state. Like Na plus gas is to be converted to Na plus aqueous, like that. Cl minus gas to be converted to Cl minus aqueous. Just a change in physical state, kind of, right? So gaseous ions are supposed to convert to aqueous ions. That is what we refer to as the hydration enthalpy. The enthalpy change happens when doing such kind of a change, right? So there, it's like this. No, the change is like gaseous ions are there. Let's say Na plus gas. Na plus gas means the gaseous stuff, right? No bonds, no considerable bonding between the particles. Gaseous. This is Na plus gas. Is going to be converted to Na plus aqueous. What is Na plus aqueous? Water molecules will be surrounded. Will surround, right? Na plus ions will be surrounded by the water molecules. See? These are the water molecules. Huh? So this is Na plus gas. Sorry, Na plus aqueous. Right? So This is all about kind of bond forming, second interaction forming. What is the kind of second interaction formed here? Iron, what is a dipole? Iron dipole interaction. So this enthalpy change involves kind of bond forming, secondary bond forming, iron dipole interaction. That means bond formings are releasing energy, exothermic. So all the delta H naught HYD values are exothermic, coming up as negative values, negative delta H naught values, right? So that is why it is said always negative exothermic, right? Right? Let's go to the things at the note level. See whether you understand clearly. Standard hydration enthalpy, delta H naught HYD, hydration, right? So enthalpy change when 1 mole of gaseous ions in the standard state, 1 mole of gaseous ions in the standard state changes into a solution with water, converted into the aqueous form, right? With concentration of 1 mole Dm minus 3. So some example, we need some example, right? If you are thinking of standard hydration enthalpy of sodium, right? If you are thinking of standard hydration enthalpy of sodium, right? Sodium plus Ca. That all means, that means Na plus gaseous ions 1 moles is to be converted to Na plus aqueous, right? That is what is meant by hydration of Na plus, right? Right now, in this case, another data is given. This aqueous form coming up with as a 1 molar solution. 1 molar solution. So normally, when considering standard states, in these standard states, if a gas is concerned, it should come up with 1 atm. Pressure is 1 atm. For solutions, the concentration is considered, that is 1 mole, right? The standard state 1 mole. So it's a solution situation, so you should come up with the 1 mole concentration, right? That is what it says, right? In your definition, that is also included, right? So just highlight the stuff, the important stuff. When 1 mole of gaseous ions in the standard state, so you can highlight 1 mole of gaseous ions, 1 mole of gaseous ions, that is where the 1 mole appears, and changes into a solution with concentration of 1 mole Dm minus 3. Changes into a solution with water, changes into a solution with water, just highlight that thing with that AQ as well. Changes into a solution with water, AQ, and of 1 mole Dm minus 3, that thing as well, right? So thing is clear. If you are to think of hydration of chloride ion, it is Cl minus gas going to Cl minus aqueous. That's it, right? For positive ions as well as negative ions, for all the kind of ions, you can think of hydration, where the gaseous ions are converted to aqueous ions with 1 molar concentration solution, right? Okay, that is hydration enthalpy. All the hydration enthalpies are exothermic because the hydrations are involving iron dipole interactions, right? You can write that thing as well. Exothermic, within brackets you can write iron dp interactions. Iron dp interactions. Those are the secondary interactions formed when hydration is to occur, right? Okay, that is all about the hydrations, right? Let's come up with the next enthalpy term, the 12th. Standard enthalpy change of dissolution. Now divided by delta H naught dis. Right? Okay. But that means that is the enthalpy change occurs, right, when you dissolve 1 mole of, right, when you dissolve 1 mole of, right, normally kind of a compound in water. When you dissolve 1 mole of considering compound in water, right, to convert to aqueous science, that is the enthalpy change occurs, right. So let's come up with that standard dissolution enthalpy, right. See, go to the definition there. Right. නැත්නම් පොඩ්ඩක් අර මේ definition එක පොඩ්ඩක් වැරදිට නේද ඇවිල්ලා තියෙන්නේ. හරි. definition එක ඇවිල්ලා තියෙන්නේ නිකන් අර කලින් definition එක උනේ දායිත් copy වෙලා තියෙන්නේ. පොඩ්ඩක් ඒක වෙනම ලියා ගමු නේද? හරි. හරි අපි පොඩ්ඩක් ඒක වෙනම ආයිත් ලියා ගමු ළමයි. හරි. Standard dissolution enthalpy, right? මෙහෙම ලියන්න. Enthalpy change when, just write that thing, right? වැරදි එකක් වෙදලා තියෙන්නේ අර hydration enthalpy එකේ කතාවම තමයි සෙට් වෙලා තියෙන්නේ. Enthalpy change when one mole of compound one mole of compound in standard state dissolved in a solvent to form a solution with the concentration of 1 mole. ඒ ටික හරිය ළමයි. මුල් ටික තමයි වෙනස් වෙන්න ඕන. One enthalpy change when 1 mole of compound in the standard state කියලා. Gaseous science කියන කයින් කරලා compound in standard state කියලා නැත්තර. Normally in A levels, right, this is regarding the ionic compounds. සාමාන්‍ය A levels වල පාවිච්චි වෙන්නේ ionic compounds වලට. හැබැයි ඒක ඕන compound එකකට පුළුවන් ඉතින්. දැන් glucose වලට පුළුවන්. හරි. glucose වලට පුළුවන්. හරි. ඒකට normal A levels වල පාවිච්චි වෙන්නේ ionic compounds වලට. හරි. So let's discuss about, let's come up with some example. Standard dissolution enthalpy. Change of NaCl solid, right? If you need to write this thing, you can write it as NaCl solid, because it's are important, reacting with a solvent. Normally in A levels we use the water as the solvent, right? If you're using the water as solvent, that will come up as aqueous science, so aqueous compound. So it could be written as like this, right? Just solid converted into aqueous state. But if it is ionic compound, one can write this one as Na plus aqueous and Cl minus aqueous as well, right? Or one can write this one as, because you know with the ionic compounds, those will convert to ions. right? Normally යන්න පුළුවන්. This is the dissolution of NaCl solid. හරිනේ? Right? That is clear. මෙතනදී H2O කියලා ලියන්න එපා ළමයි. ඒක just write it as water. If not, that will affect the mass balancing. මේක H2O කියලා ලියුවොත් ඒක mass balancing එකට affect වෙනවා. ඒ නිසා H2O කියලා ලියන්න just write the solvent in words. Right? This dissolution enthalpy. Right? ළමයි, we have a relationship. We have a relationship. Right? Among the dissolution, hydration and the lattice enthalpy. අපි ළමයි lattice enthalpy, hydration, dissolution අතර සම්බන්ධතාවක් තියෙනවා. We have a relationship among the hydration, lattice and dissolution. Right? Let's discuss about that thing. Right? Relationship between delta H naught, right, this dissolution, lattice and hydration. Right? මොකක්ද තියෙන relationship එක? හරිද? අපිට මෙන්න මෙහෙම relationship එකක් ගන්න පුළුවන් ළමයි. So let's consider, yes, the given thing. Yeah, let's consider the Ma2 solid, which is given in your note, right? Consider ionic salt Ma2 solid, right? So dissolution of Ma2 solid means converting that into aqueous ions. One can write it as Ma2 aqueous. This is delta H naught dissolution. Or as it's an ionic salt, one can write it this one as ions as well. මේ වගේ ලියන්න පුළුවන්. So this is Ma2 plus, right? Ma2 plus A minus. Ions දෙක. හරි? So you can write this one as M2 plus A minus. As you have 2 of A minuses, it should become 2. හරි? නිකන් Ma2 කියලා ලියන්න පුළුවන් නැත්නම් කොහොම ලියන්න පුළුවන්? Same form as ionic compounds, they will come as ions, right? And we can construct a Born-Haber cycle with the use of these two guys to relate the dissolution. How come? If you have to consider the lattice enthalpy of kind of an ionic solid, right? If you think of the lattice enthalpy involves solid ionic compounds, 1 mole of solid ionic compounds and the gaseous constituent ions. So if you have to come up with the gaseous constituent ions of this system, that is going to be M2 plus gas plus A minus gas, gaseous constituent ions. You have such 2 A minuses, right? So this will be related by lattice enthalpy, right? This is what actually is lattice dissociation, breaking the bonds to come up as positive and negative ions. And what is this? To convert these gaseous ions to aqueous ions, what we need to do? First we need to apply the hydration enthalpy of the cation, and then we need to apply the hydration enthalpies of anion. So this can be written as a summation of delta H naught HYD of M2 plus ion, hydration of M2 plus, just 1 mole is needed to be formed, and plus delta H naught HYD of negative ion. That is what? A minus. And such 2 moles are to be converted. so into 2, right now. So one can say this is as a whole just the HYDs as a summation, right? So HYD hydrations are always exothermic. Hydrations are always exothermic and dipole interaction forming negative values, and bond dissociations. Any bond dissociations are always endothermic bond breakings. Right? So now we can come up with the relationship. This is the initial state, this is the final state. According to Hayes law, then the changes occur when you are dealing with the same initial and final states, going to be the same. So relation of this solution is equal to this plus this delta H naught lattice dissociation plus the summation of hydration enthalpies of the cation and the anion. Right? This relationship can be taken among these three guys. See, that is clear, no? Right? So not that much questions have been asked from this in A levels, I mean in the written paper, but in MCQs this will be frequently asked. This is normally asked, right? So this means with this cycle we can say a dissolution of an ionic solid. Dissolution of an ionic solid is due to two things. Two things is due to lattice dissociation and the hydration. Right? Dissolution of an ionic solid involves two things. One thing is lattice dissociation, and the other thing is the hydration. So dissolution of an ionic solid is affected by the lattice dissociation as well as the hydration. But we have to consider both the stuff to examine the dissolution of an ionic solid, right? So that is what they are going to ask in MCQs, right? Okay. Okay, right. That is all about the stuff at the paper in the page number 5. Page number 5 වලදී ඔයාලට කතා කරේ. Right නේද? Okay. Right. ඊට පස්සේ page number 6 වල තියෙනවා මේ enthalpy change of neutralization ගැන. Just go to that. මේක ටිකක් කියව ගන්න ළමයි. Alright. Right? සාමාන්‍යයෙන් ඔයා දැනගන්න ඉන්න ඕන කාරණා ගත්තොත් දැන් මේ enthalpy change of neutralization, right? You should know that is actually enthalpy change occurs when 1 mole of H plus AQ reacts with 1 mole of OH minus AQ to form the 1 mole of liquid H2O, right? To form 1 mole of H2O starting from aqueous H plus and aqueous OH minus ions, 1 mole each, is considered as the neutralization enthalpy. That value is normally given as minus 57 kilojoules mole, right? ඒක පොඩ්ඩක් ආදාන වෙන්න ඕන කාරණයක්, right? Let's go to the stuff, right? Simple stuff there. And that neutralization enthalpy will be affected by 3 factors, right? Amount of H2O produced, more the H2O molecules to produce, more will be the heat released. And the strong weak nature of acids you are using. If you are using strong acids, no worries, but if you are using weak acids or weak bases, then the sum of the released heat will be reabsorbed to break the undissociated bonds in your weak species. That should be also calculated to come up with the final value of neutralization, right? Because neutralization එකේ final value එක decide කරද්දී විශේෂයෙන්ම ඔයා ඒකට use කරලා තියෙන acid එකයි base එකේ acidic strong weak nature එක බලපානවා. If you are coming up with the weak species, weak acids or weak base use කරලා දිනවනම් to dissociate the undissociated bonds. Weak කියලා කියන්නේ ඒකනේ. Not all the bonds are being dissociated. No? So to dissociate the undissociated bonds in your weak species, right? Some of the heat released when forming H2O molecules will be reabsorbed. So heat release will be less than, the net heat release will be less than, right, if, right, weak species is involved. So you can see the second example appearing there. හරි examples ටිකත් ඔය ගමන් බලන්නකෝ. NaOH HCl react කරලා 1 mole of H2O හැදෙනවා නම් it will produce 57 kilojoules. NaOH H2SO4 react කරලා 2 moles of H2O හැදෙන නිසා it needs 57 kilojoules into 2 as 2 moles of H2O is produced. Right ne? Third එකේ බලන්න. As a weak acid is involved there. CH3COOH AQ weak acid is involved there. Or weak acid එකක් involved වෙනවා නම් වැඩේට. හරිද? To dissociate the undissociated bonds in your weak species, right, some of the heat released, can 57 heat එක release at 57 in some of the 6 kilojoules reabsorb කරලා දිනවා to dissociate the undissociated bonds in your weak acid. So this is that 6 kilojoules is referred to as the dissociation enthalpy of the weak acid. Or 6 kilojoules can be dissociation enthalpy of the weak acid කියලා. Right, that is how the 51 value came. Right. And the neutralization enthalpy will be also affected by the, right, precipitates formed. හරි මොනවා හරි precipitate එකක් හැදෙනවා නම් ඒකිනුත් affect වෙනවා neutralization enthalpy එක. precipitate එකක් හැදෙනවා නම් ඒක නිසාත් neutralization enthalpy එක affect වෙනවා ළමයි. හරි බලන්න third example එක BaOH2 is reacted with H2SO4 to produce a barium sulfate and 2 of H2 molecules. As you are producing 2 of H2 molecules, right, 57 into 2 will be released. H2 molecules mole එකක් හැදෙන්න 57 release වෙනවා. moles දෙකක් හැදෙන්න 57 into 2 will be released. But in this case, not only producing H2O liquid but also barium sulfate solid is produced. ඒකට හදාගන්නවා barium sulfate solid වෙන්න ඕන, not the aqueous. It should be barium sulfate solid. හරි ඒ solid වෙන්න ඕන. උඩ හදාගන්න. Right, barium sulfate solid. So when forming the barium sulfate solid, there are also ionic bonds are formed. Right, barium sulfate solid කියලා ionic bonds form වෙලා තියෙන්නේ. So ionic bonds are formed. That means bond forming kind of exothermic situation. Right, exothermic situation. So not only the heat released when H2O is formed should be considered, but also the heat released in forming ionic bonds when forming barium sulfate solid is to be considered to come up with the total value of liberated heat. That is why the value is going to be greater than 114. It is the 127 the released heat. Or 114 heat release when forming 2 moles of H2O as 57 into 2. So itru value එක itru 13 kilojoules release ලා දින ළමයි when forming ionic bonds regarding the formation of barium sulfate solid. However, that is how the value of that neutralization process became minus 127 kilojoules. So with that, it is very clear the neutralization enthalpy change of an acid-base reaction will be affected by 3 factors. The first factor is the amount of number of moles of H2O to produce. When it is high, greater will be the neutralization enthalpy. The second factor is, right, whether you are using weak species, weak acids or weak bases. If you are using weak species, some of the heat release will be reabsorbed to break the undissociated bonds there, right, of the weak acid or the weak base. So that heat release will be lesser than, right, the heat release in a strong acid strong base neutralization there, right, if you are with a weak species. The third fact which will be affected is actually the formation of precipitates. If you are forming precipitates, right, there the ionic bonds will be formed, so more heat will be released there, so that that heat also will be added to the heat released by the water molecules. So that you will gain a greater value in neutralization as neutralization enthalpy is when a precipitate is to form from an acid base neutralization process, right. That is, those are the things you should know about the neutralization changes, right nේද? හරි. ඊට පස්සේ ළමයි ඔයගොල්ලෝ අර enthalpy change of reaction කියන ගම් ඔයගොල්ලෝ සාමාන්‍ය කියව ගන්න simple දේවල් ටිකක් තියෙන. අපි ඒක ගැන වෙනම කතා කරනවා question එක කතා කරද්දී. හරි. question එකට යද්දී question discussions වල අපි ගැන වෙනම කතා කරමු. right. හරි. එහෙනම් අපි දැන්ට break එකක් ගමු. right. enthalpy changes වල කතාව ඉවරයි මේ විදිහට. ඊට පස්සේ අපි next session එකේදී delta S values and delta H values ගැන කතා කරනවා අන්තිම session එක විදිහට. right. හරි. එහෙනම් පුංචි break එකක් ගමු. right? Entropy concept, right? So that is at the page number 12, right? So he had just completed the enthalpy section. So this lesson is with three major parts now. First the enthalpy, then the entropy, and then the Gibbs free energy, right? So we'll move towards the entropy, right? Entropy concept. Right. Okay. So entropy. Actually, entropy is a measure of uncertainty. Right. One can say randomness. It is a measure of uncertainty, randomness. So simply the thermal motions of the system. Right. So entropy is a measure of thermal motions of particles in the system. Right? So when thermal motions are high, we can say entropy is high. Entropy, normally denoted by the capital S, is high. But this is the idea, right? When the particles move, normally randomness also increases, right? Randomness or the disorder will also increases, right? So we can say when the randomness increases, as well as a disorder, or one can say uncertainty increases, right? Entropy will increase. So it's a measure of thermal motions of particles in the system, or one can say it's a measure of randomness or the disorder or uncertainty of the system, right? When these things increase, entropy will increase. When thermal motions increase, again particle movements are there. When the particles move, right, ordered structure will become a disordered structure. සාමාන්‍යයෙන් ඕඩ් එකක් විදිහට පිළිවෙලට දීපු දෙයක් ඒ particles move වෙන්න පටන් ගන්නතර පස්සේ ඒ පිළිවෙල නැති වෙනවා. So ordered structure becomes disordered when the particles move with the thermal motions, right? So the thermal motions and the disorder relates, right? If you are with a ordered structure, right, randomness is less. අර පිළිවෙලට මොනවා හරි දීලා තියෙනවද නේද? හිතන්න ඔයාලඟ හරි ordered structure එකක් තියෙනවා කියලා. black ball එකයි, black ball, purple ball, green ball. ඒ පිළිවෙලට ball ටිකක් set කරලා තියෙනවා කියලා හිතන්නවා. black ball ordered structure, purple ball, green ball. This is kind of an ordered structure. මේ ordered structure එකක් තියෙනවා නම්, right, uncertainty is less. ඒ කියනවා ඉතින් ordered structure එකක් තියෙනවා නම් හිතන්න, if you take a ball from this space, it is definitely going to be a green ball. No uncertainty is there. order එකක් නැත්තම් දැන් order structure එකක් තියෙනවා, uncertainty is less. When the thermal motions are not there, uncertainty is less. But when it becomes disordered, එහෙනම් බෝල් එකේ තියෙන order එකක් නැත්තම් මෙහෙන් ගන්න බෝල් එක green වෙන්නත් පුළුවන්, purple වෙන්නත් පුළුවන්, black වෙන්නත් පුළුවන්. It's not certain whether you can have a green ball if you are to come from here, if this is not an ordered structure, or when the particles are moving, right? So when the disorder happens, randomness happens. when you are with an ordered structure, then randomness is less, and disorder with the randomness is high. When the thermal motions are there, also randomness is high. Motions නැත්නම් particles මේ විදිහට ඉන්නවා. මේගොල්ලෝ හිමි move වෙන්න අතර මොකද වෙන්නේ? ඔයාගේ pick එක random වෙනවා. Right? So randomness, disorder, uncertainty even. You are not certain to pick which ball, right? So all of these are related. When the thermal motions are high, all of these three facts become high, right? So the entropy will be high. So we can say entropy is a measure of all of these things, right? Okay. So entropy is normally right given in right joules per Kelvin. Entropy is normally given in joules per Kelvin, right? Entropy is given in joules per Kelvin. අර thermal motions එක කතාවක් තියෙනවා පැහැදිලි. thermal motions වලට relate වෙන energy එක තමයි entropy කියලා කියන්නේ. particles වල thermal motions වලට involve වෙන energy එක. හරි system එකක් ගත්තට පස්සේ system එකේ energy තියෙන විධි ක්‍රම කිහිපයක් තියෙනවා. system එකක් ගත්තට පස්සේ system එකේ bonds වල system එකේ තියෙන components ලගේ bonds ඇතුලේ energy එක concentrate වෙලා නැත්තම් නේද? energy එක තියෙනවා නේද? energy එක bonds විදිහට තියෙනවා. right? ඒ වගේම energy එකකින් තවත් form එකක් තමයි kinetic energy විදිහට. thermal motions of particles. ඒකට system එකේ energy එකක් තියෙන main types දෙකක් තමයි energy involved with the bonds and energy used in thermal motions. right? එතන මෙතන entropy වලින් කතා කරන්නේ the energy of system which are used in thermal motions. Energy system which is used as bonds is discussed with the enthalpy. system එක mainly energy තියෙන ක්‍රම දෙක තමයි ඔය දෙක. හරිද? එක්ක bonds විදිහට energy එක contain වෙලා දිනනවා නැත්නම් motions වල use කරන energy විදිහට තියෙනවා. මෙතන කතා කරන්නේ entropy එකේදී the energy related to the thermal motions. kinetic energies වලට relate වෙන කට්ටිය. හරි. ඒතර මේක සාමාන්‍යයෙන් කතා කරන්නේ joules වලින්. energy related to bonds taken in kilojoules. නේ kilojoules වලින් කතා කරන්නේ. enthalpy terms කතා කරන්නේ kilojoules වලින්. මේක සාමාන්‍යයෙන් කතා කරන්නේ joules වලින්. Because these are very small particles ළමයි. හරි. These are molecular level particles. Right? Mass is very less. So the kinetic energy will be very less. Right? Mass එක බට්ට පොඩි. ඒ කියන්නේ ඒතර half mv squared එක හරි පොඩි value එකක් එන්නේ. එළම හිතන්නකෝ දැන් ඇත්තටම ඔක්සිජන් ගෑස් එකේ ඔක්සිජන් මොලිකියුල් එකේ මේ mass එක කීයද? mass of oxygen 1 molecule කීයද ගාන mass එක? एक oxygen molecule के mass की Avogadro's number of oxygen molecules 16 grams. Sorry, yeah, 16 grams. 32 grams. Avogadro's number. एक oxygen molecule है ना? ये विधान नो Avogadro number की. हर तो ढेर के mass की है. निकांग वाटे मंगे हाइम बिल्ला वाली अन्ना. तो कोड़ा निकांग वाटे पहाड़ी देशों में गारन क्या? වැඩි කිරීම 10^23 පට්ට පොඩි හොඳේ. So half mv squared is very small value, right? So the entropy value is normally given in the energy associated with those thermal motions of those like very lighter particles, molecular level particles, is given in joules. Alright? So entropy value සාමාන්‍යයෙන් දෙන්නේ joules වලින්. enthalpy value සාමාන්‍යයෙන් දෙන්නේ kilojoules වලින්. This is the energy related to thermal motions of particles in your system, right? හරි. අපිට සාමාන්‍යයෙන් අපි කතා කරන්නේ standard enthalpies කියන්නේ we are normally discussing about not just this S naught values, H naught, delta H naught values. Normally we are referring to H naught values, no? So standard entropy change, entropy values of changes are given in this joules per Kelvin per mole. So the standard amount is per mole. right? So when it comes to standard entropy or standard entropy change, the values are given in joules per Kelvin per mole, like kilojoules per mole in standard enthalpy values. Standard Q was a per mole value of it indicate conform because standard amount is 1 mole. Right now? So one can say entropy is kind of a extensive property, but entropy, the standard entropy is kind of a intensive property. Always the per mole values are referred to as intensive. Intensive intensive properties intensive properties are the properties which won't change their value with the amount of matter, right? Intensive value won't change with the amount of matter. All the molar quantities, all right, per volume quantities, per gram quantities, per mass, per volume, per mole, all those quantities are intensive properties. Extensive value depend on the amount of matter. Right? Is some introduction to the entropy concept, right? Or entropy concept, body introduction. The standard entropy change and the standard entropy, it's a intensive property, and if you are regarding to a just entropy, like just enthalpy, those are extensive properties, right? Okay. Right. Let's discuss about the factors affecting the entropy change. Factors affecting the entropy change. Factors affecting entropy as well as entropy change. Right? Okay. The first thing, physical state. Physical state. This is very clear. You know, when it comes to solid state, the particles are hardly moving. We won't see the movement of particles, right? Even though the vibrations are there, molecular vibrations are there in solid state matter, but we won't see that those vibrations right with our naked eye, right? Because those are very negligibly small, right? The movements, right? So with solids, particles are hardly moving, but when it comes to liquid, particles have some flow nature, but when it comes to gases, particles are greatly moving, right? So that means thermal motions are very heavy with the gas state and thermal motions are negligible with the solid state. So entropy is a measure of thermal motions. So we can say with the gas state you are with the greatest thermal motions with the particles, that means entropy is high with the gas state, and when it comes to solid state entropy is very low as thermal motions are very low with the particles, right? So physical state matters, right? According to physical state, thermal motion, the entropy changes. That means if you are dealing with H2O solid, it's a solid form, no? So its entropy is very low compared to the H2O gas. The same H2O is there, same chemical, but when you change the physical state, entropy will change, right? So we can say for any substance, entropy of solid state is lesser than the entropy of liquid state, and entropy of gas state is very high compared to these two situations. You know, with gases, right, the molecules, the particles are moving here and there, right, with very high speeds compared to the liquid and solids, right? And the randomness and all the things, uncertainty, all the things are greater with the gas molecules, gaseous system compared to solids and liquids, right? So physical state matters, right? What else? So we know when changing the pressures temperatures as well as volumes, right? We can think of some change between physical changes, right? We can think of some physical changes when increasing the change in the temperatures, pressures and volumes. So pressures, volumes and temperatures as well affect the entropy, right? So it's like this, no? So the thing is, so you may have a solid, right? Solid that can be converted to a liquid particles are here and they are moving, right, like this, by increasing temperature. So here the entropy is low and entropy is bit high here, and we can convert this liquid to a gas where the particles are very highly moving by changing temperature. Right? So temperature will affect the entropy. That means you can say when the temperature is increased, as thermal motions increase, right? A temperature is the kinetic change, right? As temperature increases, right? When thermal motion increases, so one can say when solid goes to a liquid and goes to a gas again, right? So one can say the entropy will increase, right? Temperature will be affected. So temperature will affect the entropy. How come? When temperature is increased, thermal motions will increase, so one can say solid will turn to liquid, liquid convert to gases. That means ultimately entropy will increase. Alright. Third thing, with pressures as well, we can think of phase changes. Pressure phase changes come පුළුවන්. If you have to increase the pressure, gas converts to liquid, liquid converts to solids. So that is how the pressure affects. So when pressure is decreased, you can convert the solid to liquid, liquid to gas. That means entropy increases. The opposite as the temperature. Right now? What else affects the entropy? Volume as well. One can say molar volume even. Right? So what about the volume? Here the volume is low. Right? The particles are in a smaller volume. The considering amount of particles, let's say 1 mole of particles, are in a smaller space. Space occupied by 1 mole of particles is less. When it comes to gases, space occupied by 1 mole of particles are high. Right? So that means volume increases means it looks like converting a solid to a liquid to a gas. Right? So volume is increasing means it is like going from a solid to a gas. Right? So that when going from solid to a gas, as the entropy increases, we can say as volume increases, the entropy will increase. හරිද? volume එක වැඩි කරනවා කියන්නේ හරියට solid එක ක්‍රමයෙන් gas එකක් විදියට convert වෙනවා වගේ තමයි. solid එක gas එකක් වෙද්දී entropy එක වැඩි නිසා අපිට කියන්න පුළුවන් volume එක වැඩි කරද්දී entropy එක වැඩි වෙනවා. හරිද? Right. What else? Amount of matter that also affected. That also will affect the entropy. Right? අර එකක් තරම තමයි. හරි? Kinetic change of system. මතකනේ kinetic change of system. is CO2 nRT. How many? Hari? Amount of matter වැඩි වෙද්දි kinetic energy වැඩි වෙනවා. Right? Total kinetic energy is this ne? Ke bar is the 3 by 2 RT, average kinetic energy. But this is total kinetic energy. It is 3 by 2 nRT. In a number of moles වැඩි වෙද්දි kinetic energy thermal motions වැඩි වෙනවා. Energy involved in the thermal motions increase. That means entropy increases. Right? That is what it says ne? Early. Right? So when amount of matter increases, kinetic energy involved in motions increase. That means entropy increase. Entropy is all about the energy involved in thermal motions. Kinetic energy is involved in thermal motions. Right? Okay. Another thing, effects. The pure mixed nature. That will also affect the entropy. That will affect the randomness. That will affect towards the randomness, right? So when mixed nature increases, we can say entropy increases. If you have a mixture, rather than coming up with a pure state, you will come across more uncertainty with the mixture. හරි ඒක පැහැදිලි මේ හිතන්න මෙහෙම දැන් ඔයාලඟ තියෙනවා kind of this හරි මෙතනින් මෙහෙම වහලා තියෙන්නේ close කරපු vessel එක තියෙනවා හරි purple balls උයි හරි green balls උයි තියෙනවා හරිද so this is an example for pure substance. Pure. Only one kind of substance is appearing at the considered space. What you do is you just open the thing here. So what will happen? Then you will come up with a mixture. You come up with a mixture. These balls get mixed, right? This is example of pure state, this is example of mixture. So the uncertainty is, actually you can clearly see now, the uncertainty is high here. So if you are to take a ball from this space, let's say these are moving balls, right? Moving gas particles. If you take a gas particle from here, definitely it is going to be a green color particle. No uncertainty there. This is definitely going to be a purple color gas molecule. No uncertainty there, right? But if you are to take a ball from here, as these are moving particles, right? So from this portion, it could be a green color thing or a purple color thing. So uncertainty is there. Greater uncertainty when you have a mixture. Right? That means entropy is high when you are with a mixture. So when the mixture energy is high, entropy is high. Right? Okay. That is the sixth fact affecting the entropy. Right? So entropy is high here. Entropy is less here. Right? Now? Okay. Those things are concerned there. So those are the factors affecting the entropy. Right? Now? Okay. Then these will be needed when following doing those MCQs, some MCQs, right? As well as some essay questions. You may come across these ideas, right? මේ වගේ නම් හුඟක් ඉන්නවලු මේක වගේ මොකක්ද අහන්න ප්‍රශ්න. මේක MCQs වල හැගේ අහන්න පුළුවන්. අනිත් වෙන වැඩි ඇහෙන්නේ නැහැ. මේ තුන හුඟක් questions වල අහනවා, right? Then next point with the entropy. Entropy is a state function. right? Entropy is a state function. I'll write it here, right? Like enthalpy, entropy is a state function. Entropy is a state function. That means the change in the entropy only depends on initial and final state. That is what it means, right? State function के लिए क्या हुआ? Change depend only on initial and final states. Path taken is no use, right? Energy depends only on initial and final states. So that we can write the change in entropy only depends on initial and final states. So S final minus S initial. Like in enthalpy changes, we can write like this. When it comes to a chemical reaction, the final state means it is the product state, initial state means it is the reactant state. In a reaction means reactants converted in products, no? That means reactants are the initial state, products are the final state. So final means the products, initial means the reactants. So as entropy is a state function, we can come up with this relationship. Entropy change of a reaction can be calculated by taking the summation of the entropy values of products and minus the summation of entropy values of reactants, right? Okay, remember that this is not like the enthalpy situation. You don't have a delta here. Normally when enthalpy things are considered, delta H naught R is equal to delta H naught F products minus delta H naught F reactants. That is how this kind of a reaction appears with the enthalpy changes. But you don't see the appearance of delta terms in enthalpy things. In entropy things, right? There is a knowledge to gather from that thing, Lamai. Actually, that is happening because entropy is with a absolute value. So you have a absolute zero for entropy. You have absolute zero for entropy. You have an absolute condition. There is a condition where all the thermal motions become zero. What is that situation? That is when the temperature is Kelvin 0. That is when temperature is Kelvin 0. Right? At the Kelvin 0, no thermal motions with the particles. So there the thermal motions become 0. That means entropy is 0. So related to that 0 situation, the entropy values are given. Right? So entropy is with the absolute value. So that is why we write like this. But when it comes to enthalpy, that is not the case. When it comes to enthalpy, you are unable to measure the absolute value of enthalpies. What you do is reference to the reference form. With respect to the reference form, the enthalpy values are measured. As we are unable to measure the absolute value of enthalpy, what we do is we just assume the enthalpy value of the reference forms, most abundant elements, elemental form is assumed as 0. Right? With respect to that, the enthalpy values are given. That is why a delta thing is used. Change is measured. But here you have absolute. So if you have written some delta here and here, right? they won't give you marks, right? මේක ලියද්දි ඩෙල්ටා ලියන්න එපා හොඳ. ස්ටෑන්ඩඩ් වුණොත් මේක නෝට් එකක් එක්ක එනවා, right? හරි ස්ටෑන්ඩඩ් වුණොත් නෝට් එකක් එක්ක එනවා, right? Okay, right, that is what it says, right? හරි ඊට පස්සේ කතාව next point, predicting the sign of delta S naught R delta S R of a reaction. හරි reaction හදුනොත් ඒකේ sign එක කොහොම predict කරන්නේ? For that lamai normally we use this thing. With the use of this knowledge we can predict the sign of delta S, right? We can use, predict the sign of delta S with the use of this knowledge of a reaction. Let's come up with some examples. හිතන්න මෙන්න මේ වගේ example එකක් දැක්කම, right? Let's predicting sign of delta S. The sign of delta S naught R. Right? Let's take some examples. Right? Let's take this example, this reaction. Calcium carbonate decomposition. You use the calcium oxide plus CO2 gas. Right? We are supposed to predict the sign of delta S here. Just what you need to do is apply this theory. It's like this. So at this side you don't have gas molecules. So number of gas molecules at this side equals 0. At this side number of gas molecules here you don't have, but you have one here, the gas molecules, right? Just one. So going from reactant to products, number of gas molecules increase, right? When more gas molecules are there, that means more your entropies, more your thermal molecules, more your entropies. So one can say, as number of gas molecules are less here, your entropy is less here, and as number of gas molecules are high here compared to this, your entropy is high here. So going from reactant to products, your entropy has increased. That means your delta S is positive. Your delta S is positive. So as S increased, delta S is positive. Right now? Okay. So delta S positive means S increased. Some delta property, let's say, is the delta X positive means going from reactant products, the property X increased. That is the simple idea. Delta X negative means going from reactant products, the property X decreased. Right? That is the idea. So that means when the property increased, that means delta value should be positive. The other way around. Right? Right. Let's come up with another example. Right? So sign of delta S of a reaction can be predicted by just seeing the number of gas molecules appearing with the two sides. Another example. Let's come up with another example. Right? Kind of this. N2 gas reacting with H2 gas to produce the NH3 gas. Right? Let's discuss the sign of delta S here. Here number of gas molecules one plus 3, it is 4. It's 4. At this side, product sides, number of gas molecules 2. See, more gas molecules are there means more will be your entropy. Less gas molecules are there means will be your entropy. Right? More the gas molecules, more will be the thermal motions with those particles. More will be the kinetic energies with the particles. So that entropy will be high there. Right? So we can say going from reactant products, entropy decreases. Entropy decreases. As entropy decreases, you can say sign of delta S is negative. Right now, as entropy decreases, delta S is negative. Right now. Okay, that is how we are supposed to predict the sign of delta S by looking at the number of gas molecules in reactant and product sites. Right now, thing is clear. So that is indicated there. Let's go to the point there. It is said predicting the sign of delta S R of a reaction when going from reactant products. If number of gas molecules increase like this, entropy increases so that the entropy change is positive. Sign is positive. If number of gas molecules decrease like this, entropy increases so that the delta S value is negative. Clear, no? Right. The next thing we should know about the entropy. Right? We'll quickly go to the theory part, and then we can do some question at the end. Right? Next one. Now we are going to discuss about sign of delta H R, that means enthalpy change of reaction, and the sign of delta S surrounding. Entropy change of system, surrounding. Right? We have relationship between the sign of delta H R and the delta S surrounding. Right? This is about that thing. Right? We are just quickly going to the theory. You should know, right? So if delta H not R is negative, that means exothermic reaction is happening at the system. Let's see what will happen to the surrounding delta S not surrounding. So the system looks like this. So system, there is no negative reaction happening there. That means system will release heat to surrounding. Right? So that means when it comes to surrounding, its temperature will increase as system has released some heat to surrounding, temperature of the surrounding will increase. So thermal motions of particles in surrounding will increase, right? As temperature of the surrounding increases, thermal motion of particles in surrounding will increase. So entropy of surrounding that means delta S not surrounding sorry, the entropy surrounding, S surrounding will increase. That means delta S surrounding is positive, right? Entropy increases means delta S is positive. The same idea like this, right? 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 ඒ කියනවා සිස්ටම් එකේ එක්සොතර්මික් රියැක්ෂන් එකක් වෙනවා නම් ඔයාගේ සරවුන්ඩින් ගේ එන්ට්‍රොපි එක වැඩි වෙනවා, right? If kind of exothermic reaction occurring in your system, right, the entropy of surrounding will increase, delta S surrounding becomes positive. ඕක මෙහා පැත්තට කතා කරමුද? What if kind of endothermic reaction occur in your system? If delta H naught R is positive, so situation is looks like this. So you have system, delta H is positive. That means system absorb heat from the surrounding. System absorb heat from the surrounding. Endothermic, right? Then what will happen to the surrounding? The temperature of surrounding decreases. Temperature surrounding decreases. As temperature is absorbed to the system, temperature of surrounding decreases. So thermal motions of particles of surrounding decreases. As temperature increases in the surrounding, thermal motions of particles will decrease in the surrounding. Right, in surrounding decreases. That means entropy of surrounding decreases. Entropy decreases means delta S is negative. Entropy decreases means delta entropy negative. Right now? So if kind of a endothermic reaction is occurring in your system, right? Entropy of surrounding decreases. Entropy of surrounding coming up with a negative value. Right now? Just complete the stuff there. This other page 12. That is the relationship between the enthalpy change of the reaction and the entropy change of the surrounding, right? Okay, nida. Hari. කිව්ව තමයි මම ඔයා entropy change එක ගැන දන්නගෙන ඉන්න ඕන කාරණා ටික. theory පැත්ත. හරි? entropy change එක දැනගන්න ඕන theory ටික තමයි කතා කරේ. හරි? problem solving වලට නම් ඕන කරන්නේ entropy පැත්තේදී problem solving වලට AC equation problem solving වලට ඕන කරන්නේ අර delta S not R is equal to S not products minus S not reactant කියන relation එක විතරයි. ඒක විතරයි ඕන කරන්නේ. හරි? අනිත් ටික theory part එක. අපි ඒක involve කරගෙන question එකක් හදමු Gibbs කතාවත් ඉවර වෙලා. හරි? Gibbs ගැන පොඩි පොඩි theory ටිකක් තියෙන. ඒ ටික කතා කරලා ඉවරලා Gibbs උයි entropy දෙකම අල්ලලා question එකක් හදමු. right? එතකොට මේ පැත්ත ඉවර නිසා. right? හරි. අපි ඔහොම Gibbs කතාවට යන්නද? හරි gibbs කතාවටත් යන්න දුමුඩක් ගාලා හරිනේ right හරි ළමයි entropy වලට මම කලින් කිව්වා වගේ entropy වලින් problem solving එකත් අපි කියනවා essay question solving වලට ඕන කරන්නේ මේ equation විතරයි. මේක දන්නවා නම් ඒ essay question solving එක සාමාන්‍යයෙන් කරගන්න පුළුවන්. මේකයි සාමාන්‍යයෙන් මෙන්න මේවා කැලිය අහනවා. මේ කැල ගොඩක් අහනවා. right මේකයි හරි මේ කොටසයි ඔයාලට මේකයි පුළුවන් නම් සාමාන්‍ය essay question එක solve කරගන්න පුළුවන්. හරි අපි ඉස්සර question එක කරලා බලමු ඒක සම්බන්ධයෙන්. අපි යමු එහෙනම් Gibbs free energy එකට. ඒක ඉවර කරලා question එකට යන්න පොඩි question එකට යන්න. Let's come towards the next subtopic. That is Gibbs free energy. Concept of Gibbs free energy. Right, බලමු. Gibbs free energy, right? Okay. Right? Actually, Gibbs free energy gives you some idea about the total energy in your system. System එකේ සම්පූර්ණ energy ගැන idea එකක් තමයි Gibbs free energy එකෙන් දෙන්නේ. හරිද? Normally, the two forms of the energies involved with your systems are actually energies involving with the bonds, right, which is given by the enthalpy values, and the energies involving with the thermal motions of the particles, movements, right, that will be given by the entropy values. So, Gibbs free energy is another kind of state function which combines the two, so that it will be given as H minus Ts. So this is the fundamental equation giving you the Gibbs free energy, right, which is also a state function which gives you the idea of the total energy of the system, right. Then මෙතන ළමයි මේකේ හරි the two forms, right, sometimes when you break the bonds and release the energies, that will increase the thermal motion systems, right. तर අර H value එක minus වෙනකොට thermal motions වැඩි වෙන්න පුළුවන්. H value එක අඩු වෙනකොට thermal motions අඩු වෙන්න පුළුවන්. So those are related. Anyway, this equation gives you the net energy involvement in your system, right. This portion gives you the idea of energy involved in the bonding energy, right, inside bonds, and this gives you some idea about the energy involvement in the involvement of motions of the particles, right, or moving particles, right. Alright. So, and Gibbs free energy is considered as a state function, remember that, right. Gibbs free energy is also a state function, right. Okay, Gibbs free energy is a state function. What is a state function? State function means right, change, right, only depends on initial and final states of the system, right? So that is what a state function means, right? So as it's a state function, right, we can write a equation like this for the Gibbs free energy. Delta G R, or delta G, let's say, is equal to delta G final minus delta G initial, right? We can write an equation like this, right? That is a state function, right? So if you are regarding a reaction, this becomes delta G R. For a reaction, the final state is the product state. And initial state is the reactant state. So normally we can write it as the F values of products minus the formation values of reactants, right? So this equation also can be used to find out the delta G, the Gibbs free energy change of a reaction, right? So in this case as well, you have some delta values here, not like in the entropy thing. Like in enthalpy thing, delta values are appearing. That is very clear because as in enthalpy, you can't come up with an absolute value for Gibbs free energy. Enthalpy absolute value එකක් දෙන්න බැර නම් Gibbs free energy absolute value එකක් දෙන්න බෑ ළම. මේක absolute value එකක් තියෙනවා. temperature Kelvin 0 ගත්තත් මෙයා 0. ඒක හරි. Kelvin 0 වල මෙයා 0 ඒක හරි. හැබැයි මෙයාට value එකක් තියෙනවනේ bounds තියෙනවනේ bounds IPA වෙනවනේ Kelvin 0 වල. ඒතකොට මෙයාටත් value එකක් තියෙනවනේ. මේ value එක ඉතින් හොයාගන්න විදියක් නැහැනේ. right? ඒක නිසා there is no absolute point as 0 for Gibbs free energy as well, as absolute value for H is not mentioned, right? Can't be found, right? So you have to come up with the delta sign here at this equation, right? Delta H වගේ තමයි. හරි. එතකොට ඔයාට delta ඔයාට Gibbs free energy change එකක් හොයන්න ඔයාට මේ equation use කරන්න පුළුවන් බය නැතුව, right? If you need to come up with the Gibbs free energy change of a constrained reaction, you can use this thing as it's a state function, right? What is the other equation available to come up with the Gibbs free energy change? That is actually coming from here, from the fundamentals. From the fundamentals, another equation is there to come up with the Gibbs energy change. Gibbs energy change. For a change occurring at, for a change occurs at constant temperature and pressure, another equation is there to find the Gibbs free energy change. That is coming from the fundamentals, delta G is equal to delta H minus, as the temperature is kept constant, it's a constant value, it is not a change, it's a constant value, T delta S, right? These are changes, but this is a constant, right? This can be applied only when the pressure and the temperature of the system is kept at a constant value, or throughout the experiment or throughout the reaction, the pressure and the temperature should be kept constant to apply this equation. pressure එකයි temperature එක constant තියාගත්ත reaction එක, so if the throughout the reaction, if you had kept the temperature and pressure at a constant value, then you can apply this thing to come up with the Gibbs free energy change. හරිද? පැහැදිලි? ඉතින් ළමයි අනිවාර්යයෙන්ම මේ equation එකෙන් ඔයාට Gibbs free energy change එක හොයන්න නම් pressure එක constant තියෙන්න ඕනේ. Without a constant pressure, the delta H values are not defined. Delta H means the heat change occurred in a constant pressure process, right? From a definition delta H. Heat change occurred in a constant pressure process. That is what delta H means. So to define a delta H value, definitely pressure should be kept at a constant value. And this equation clearly says, right, this T is not coming up as a delta T. This T is there. So just one value can be written here. That is a constant. That is the constant temperature, right? So as even though you see some changes here, T comes up with a single value, just T, right? So the temperature should be kept at a constant value, right? Alright, ඉතින් ඔහොම delta G හොම්ලද delta G හොයන්න question එක මේ forms දෙකෙන් කැමති එකක් ඔයාලට පාවිච්චි කරන්න පුළුවන්. මේ data දීලා තියෙන විදිහට මේ equation දෙකෙන් කැමති එකක් පාවිච්චි කරන්න පුළුවන්, right? Right, okay. Let's go to the points there at your page number 30. Burn. මුලින් කියලා දෙන මෙහෙම නේද? Gibbs free energy is a state function which combines enthalpy and the entropy. G is equal to H minus Ts, and that will leads you to this equation. Delta G at constant temperature and pressure is equal to delta H minus T delta S. Gibbs free energy is a state function, so that you can come up with this regime as well, right? Okay. Then by looking at the sign of the delta G, right, this can be used to predict the spontaneity of a reaction, right? So that is the next point you should know about the Gibbs free energy, right? So sign of delta G in a constant temperature pressure process, it is very important, no? Can be used to predict the spontaneity of the processor's reaction. What is meant by this term spontaneity? What is that idea? The idea is Islam. At that considering temperature and pressure, when reaction occurs without supplying energy from the outside, as soon as the reactants brought together, such a process is referred to as a spontaneous process, right? That is the idea there, idea of spontaneity, right? Spontaneous process means at constant temperature and pressure, if the reaction occurs without supplying energy from the outside, as soon as reactants are brought together, then such a process is referred to as a spontaneous process. Sometimes when you keep the temperature and pressure constant, right? Sometimes when you put the reactants together, change won't occur without supplying energy from the outside, right? So if you are thinking of electrolytic processes, right? Electrolysis of a copper sulfate solution, without supplying energy from the outside, without supplying energy from a battery, the copper won't get deposited at the cathode. Gas bubbles won't liberate from the anode. The change won't occur without supplying energy from the outside. So copper sulfate aqueous convert into copper solid and releasing O2 gas. That reaction is non-spontaneous at room conditions, at room temperature and 1 atm pressure, right? To do that reaction, you definitely need to right? Use some energy from the outside, right? That is the meaning, right? If a reaction occurs without supplying the energy from outside, as reactants are to bond together at constant temperature and pressure, those are referred to as spontaneous processes, if not non-spontaneous. Sometimes to do some processes, you need to supply temperature. See? So if you are thinking of lead chloride, if you are thinking of lead chloride at 25 Celsius, dissolved in the lead chloride to Pb2 plus aqueous and Cl minus aqueous, this process, this reaction, this change, actually this change is not happening at 25 Celsius. At 25 Celsius, this won't happen. Constant temperature 25. 25 Celsius 180 won't happen. So non-spontaneous at 25 Celsius and 180. But if you are to heat the stuff maybe to 80 Celsius, what happens? This happens when PbCl2 dissolves. මතක නේද? lead halides රත් කරාම dissolve වෙනවා. ආයෙත් cool කරාම precipitate වෙනවා. Right? At 80 Celsius happens. So one can say spontaneous at 80 Celsius. හරි? ඒ කියන්නේ 25 නම් ටෙම්පරේචර් එකක් තියන්නේ. ඔයාගේ කාමරේ උෂ්ණත්වය 25 Celsius නම් මේ ප්‍රොසෙස් එක වෙන්නේ නැහැ. ඔයා මේක භාජන මොකක් හරි විසිල් එකකට දාලා තියෙනවනේ 80 Celsius මේන්ටේන් කරන විසිල් එකකට. ඔයාගේ ළඟ oven එකක් තියෙන 80 Celsius වල තියෙන. අපි හිතන්නේ ovens දෙකක් තියෙන. එකක් තියෙන 25 Celsius වල. අනිත් තියෙන 80 Celsius වල. 25 Celsius තියෙන oven එකට lead chloride solid එකක් දානවා. මේක වෙනවද? වෙන්නේ නැහැ. හැබැයි ඔයා 80 Celsius මේන්ටේන් කරන oven එකට දානවා මේ lead chloride precipitate එකම. මොකද වෙන්නේ? dissolve වෙනවා. Without supplying energy from the outside, that happens in 80 Celsius oven. Alright? But in 25 Celsius oven, that won't happen. That is the idea. Right? Spontaneity means that if without supplying energy from the outside, with that considering conditions, temperature and pressures, if the reaction happens when the reactants are brought together, those are spontaneous processes. If reaction won't happen, those are non-spontaneous processes. Right? Right? So that is what spontaneous means, spontaneity. Right? So we can use the sign of delta G to predict the spontaneity. Right? So if the temperature and pressure is kept constant for a process and if it occurs spontaneously, right, we say the sign of delta G is negative. Sign of delta G is negative. That is very clear now. That is not rocket science, right? That is very clear science, right? Why is that? G is all about the energy content of the system. Delta G negative කියන්නේ මොකක්ද? That means energy decreases, gives free energy decreases. Delta G negative gives free energy decreases. Always system tries to decrease the energy to get stabilized. හරි? කට්ටිය කැමති එනර්ජි එක අඩු කරගන්න. අඩු කරාම එයා ස්ටේබල් වෙනවා. හරි? එහෙනම් එහෙම දේවල් ස්පොන්ටේනියස් නිකම්ම සිද්ධ වෙනවා. මම මහන්සි වෙලා කරන්න ඕනේ ඕන කෙනෙක් කැමති ස්ටේබල් වෙන්න. Everyone likes to become stable. ආයෙත් එළියෙන් මුකුත් එනර්ජි දාන්න ඕනේ නැහැ. එයා ඉතින් නිකම්ම ස්ටේබල්. If the delta G is negative for a process, if the delta G is negative for a process, that means when the process happening, the energy of the system decreases. That means system becomes more stable. So no need to supply energy from the outside to for a system to convert to a stable state. System itself do that thing as the system is more keen to become stable. If delta G is positive, what that means? Delta G positive කියන එකේ තේරුම මොකක්ද? When the process occurs, energy increases, G increases. Again, system becomes unstable. Systems are not keen to become unstable, right? System become unstable and කැමති නෑ. ඒ නිසා we have to supply energy. අපිට එළියෙන් වැඩක් කරලා තමයි ඌ unstable කරන්නේ. Stable ඉන්න එකෙක් නිකන් unstable ඉන්න කැමති නෑ. ඌ unstable කරන්න ඕන නම් if you need to increase the energy of the system, definitely you have to do some work from outside. අර ඔකයි අදහස, right? So that we can say if the delta G is negative, energy decreases, that means spontaneously those processes will occur. If delta G is positive, that means energy increases, that means become unstable, so those are non-spontaneous, spontaneously those won't occur. Right නේද? unstable එක කැමති නෑ. එහෙනම් ඒක අපිට use කරන්න පුළුවන්. හරි? එහෙනම් that is how the sign of the delta G is used in deciding spontaneity, right? So if delta G is negative, spontaneously such processes occur. Without supplying energy, the system will definitely do that process as it becomes stable then. Right? Reaction, if you are considering reaction of the process is spontaneous. If delta G is positive, that means by doing the process, system becomes unstable. Energy එක වැඩි වෙනවා. G කියන්නේ energy එක වැඩි වෙනවා. Unstable වෙන්නේ එහෙම දේවල් යා නිකම්ම කරගන්නේ නැහැ. නිකම්ම spontaneously එක වෙන්නේ නැහැ. So reaction is non-spontaneous. If delta G is 0, plus උත් නැත්නම් negative නැත්නම් 0 නම් අපි ඊළඟට කියනවා the reaction or the system is at equilibrium කියලා. Right? Normally this if you need some examples for equilibrium systems, right? Systems at phase changes. This is some very frequently used example. That means at melting point, right? Solid liquid equilibrium appears now. At boiling point, then phase changes occur. Systems at phase changes clearly represent the systems at equilibrium when liquid converts to gas. H2O කියන එක 0 celsius වල දී delta G 0. H2O කියන system එකේ 100 celsius වලදී delta G 0. Right? Phase changes වෙන situations වලදී delta G 0. හරි නේද? හරි ඒ ටික දැනගන්න ඕන. But these are very important. This is how we can predict the spontaneous reaction by looking at the sign of delta G. Alright. අපි මේ වගේ example එකක් කරමු තවඩ එයි. අන්තිම question එක විදියට. හරි. තව මොකද දැනගන්න ඕනේ මොකද්ද? අර අපි කිව්වා වගේ ළමයි මේ delta G ගේ sign එක දිහා බලලා අපිට spontaneity එක decide කරන්න පුළුවන්. Right? delta G ගේ sign එක අතරම ළමයි delta G ගේ sign එක අතරම ළමයි delta H ගේ delta S ගේ sides වල decide වෙනවා. By looking at the sign of the delta G, we can predict the spontaneity of the reaction. As sign of delta G is depending on the sign of delta H and delta S as well as temperature, right? By concerning signs of delta H, delta S and temperature, also we should be able to predict the sign of delta G as well, so that the spontaneity of the reaction. හරිද? delta G ගේ sign එක දිහා බලලා අපිට reaction එක spontaneity ගැන comment කරන්න පුළුවන්. delta G ගේ sign එක delta H ගේ sign එකයි delta S ගේ sign එකයි ඒ වගේම temperature එකත් මත depend වෙන නිසා by considering the sign of delta H, delta S and T, we should be able to comment on the sign of delta G so that the spontaneous reaction. Right now? හරි. එහෙනම් බලමු මේ වැඩේ කොහොමද කරන්න කියලා. Right? That is the next point, ultimate theory part we need to learn here, right? Commenting, right, on the spontaneity, or one can say sign of delta G, right, depending on signs of delta H and delta S. Now we are going to use the signs of delta H and delta S to come up with the sign of delta G so that the spontaneous reaction, right? Yes, the first situation, we have such 4 situations. Let's come up with the first situation. When delta H is negative and delta S is also positive, that is the first consideration. ආගේ මුලින්ම තියෙන්නේ ඒක. අපි කතා කරන් තියෙන්නේ. අපි දෙවෙනි කතා කරනවා when delta H AB කියලා තියෙන්නේ. ටියුටි තියෙන විදිහම ගමු. B is when delta H is positive and delta S is negative. හරි. බලමු මේ සිටුේෂන් දෙක අපි කොහොමද හැන්ඩල් කරගන්නේ කියලා. හරි. මෙන්න මේ පොඩි වර්කින් එකක් කරන්න. Hurry. See, let's copy this working. We know delta H minus T delta S is equal to delta G, right? The sign of delta H is negative, sign of delta S is positive. When it is positive, this whole stuff becomes negative. Alright? T කියන එක හැමදාම positive value එකක් ළමයි. Temperature කියන එක හැමදාම positive value එකක්. Right? Absolute temperature can't have a negative value. So Lama, here the T is, I forgot to mention, right? This T is absolute temperature. That means Kelvin temperature, right? So temperature can't have negative value. Kelvin 0 values. So this one is also positive value, so that this multiplication will give you the sign plus and minus is minus. So you are supposed to add a negative value to the negative value. You are supposed to add a negative value to the negative value. So G will always be a negative value then. Right? So reaction is always spontaneous under these conditions, right? Irrespective of the temperature. Delta G is negative, that means reaction is spontaneous. Reaction is always spontaneous. आधार reaction එක delta H negative වුණා, delta S positive වුණා, අනිවාර්යයෙන්ම reaction එක spontaneous. Temperature මොකක් වුණත්. With any temperature, right? Reaction is spontaneous. Right? අපි ඔය වගේම working එකක් කරලා බලමු. ඊළඟ condition එක මොකද වෙන්නේ කියලා. When the delta H is positive and delta S is negative. But delta H is positive, delta S is negative. So this whole stuff coming up as positive. Negative, negative, positive. So mono temperature ගත්තත් irrespective of the temperature, delta G is always positive. You are adding a positive value to a positive value, adding a positive value to a positive value, right? So the sign of delta G, so that the spontaneous reaction won't depend on temperature, right? With these two situations, right? Reaction is always non-spontaneous. Reaction non-spontaneous නම් කොච්චර temperature අඩු වැඩි කරත් ඔයාලට spontaneous කරගන්න මේ reaction වෙන්නේ නැහැ. හරිද? අනිත් දෙකත් ඔහොම බලමුද? Right? What happens when the delta H and delta S both are negative? බලන්න කොයි වගේ සිටුේෂන් එකක් වෙන්නේ කියලා සෝට ස්පොන්ටේනිටි එකට. We know the delta H minus T delta S is equal to delta G, right? So this is negative, this becomes positive, so that you are adding a positive value to a negative value. You are adding a positive value to a negative value. So if this positive value is high, then delta G is going to be a positive. If this positive value is low than this, delta G is going to be a negative. Right? So delta G could appear as positive or negative when the delta H is negative and delta S is negative. So whether delta G appears as a positive or negative will depend on temperature, then depend on whether this one is greater than this or this one is lesser than this. That will be depending on the temperature using. If you are using a greater temperature, this positive value will be greater, right? So that delta G is going to be a positive value. If you are using a lower temperature, smaller temperature, this positive value will be smaller, so that this will be smaller than this, so that value will be negative for the delta G. So that depends on the temperature then, right? So at higher temperatures, right, we can write this stuff like this: T delta S is negative, right? As the temperature is high, right? So positive value is high, so delta G is positive. Right? Reaction is non-spontaneous. Right? But at lower temperatures, right, if you do the working again, this is negative, no? So this whole stuff become positive. Right? At lower temperatures, this positive value will be low. That means that positive value will be lower than the negative value here. So the summation will become a negative. Right? It's non-spontaneous. Spontaneous. So at lower temperatures, as delta G if it becomes negative, reaction is spontaneous. Right now, that is how temperature will affect the spontaneous reaction if delta H and delta S both carry negative values. So opposite signs තියෙනවා ළමයි delta G sign එකට නැත්නම් spontaneity එකට temperature affect වෙන්නේ නැහැ. Same sign තියෙනවා නම් දෙන්නටම temperature එක affect වෙනවා හරියට. Just do the fourth one as well. හතරවෙනි එකත් ඔය විදිහටම කරා. D when the delta H and delta S both coming as up as positive values. Do the working. When delta H is positive and delta S is also positive. මොකද වෙන්නේ? See, this is positive, this is also positive. This becomes negative. So that delta G could be positive or negative. Adding a negative value to a positive value means it could be negative or positive. If the temperature is high, that means this negative value will be high than this value, positive value. So delta G becomes negative. If temperature is low, that means this negative value will be low, maybe lower than the delta H, the positive value here. So that this becomes positive. Right? So we can say sign of delta G, that means spontaneity of reaction, depends on temperature. How come? See, at higher temperatures, first thing is about higher temperature. No? Right? Delta H minus T delta S. It's positive, is positive. At high temperature, what happens? The temperature is high, negative value becomes higher. That means it will be higher than the positive value. That means negative value means reaction is spontaneous. Right? at lower temperatures? Let's apply the situation. This is positive as well as this one. When you are dealing with a lower temperature, this negative value will be low, so that lower than the positive value here, so that positive value wins. Non-spontaneous. So as delta G becoming positive, reaction becomes non-spontaneous. Right now, හරි. ඉතින් ඔහොම තමයි අපි සයින්ස් යූස් කරන්නේ ඩෙල්ටා ඩෙල්ටාස් ලගේ රියැක්ෂන් එක ප්‍රෙඩික්ට් කරන්න රියැක්ෂන් ස්පොන්ටේනියස් එක ප්‍රෙඩික්ට් කරන්න. හරි. රයිට්. ඊට පස්සේ පොඩි ක්වෙස්චන් එකක් කරමු අපි මේ සම්බන්ධයෙන්. ඕගොල්ලන්ට last 5 years වල questions ටික තියෙනවා. ඔයාලා page number 17 onwards ඉස්සි question ටික. දැන් 20 වගේ දැන් පටන් ගන්න ටික. හරිද? එතකොට මේ MCQs ටිකක් තියෙනවා ඔයාගේ page number 14 වල ඉඳන් ඉස්සරහට last 5 years වල. හරි? ඒ ටික ඉදදී කරන්න. හරි? අද අපි එක question එකක් කරමු ළමයි මේ අර වැඩි පටන් ගන්න simple question එක විදියට. right මේ මම ඕගොල්ලෝ ළමයි last 5 years වල නෙවෙයි ඉතුරු questions එක ගෙනාවා. right 10 years වගේ කරන්න යන්නේ. හරි? Hari, okay lamai first question ek karamuda. Let's do the first question. I'll give you few minutes, maybe 5 minutes to do the first question, 2011 question. Hari, lamai questions ek karanna. මේකේ මේ අන්තිම අවුරුදු පහේ questions එක අපි night session වල කරමු. last week එකේ night session එක අපි කරේ නැහැ. ඒකේ වීඩියෝ එකක් එවන්න. හරිද මේ එතකොට මේ Wednesday next හෙට tomorrow we'll do the last 5 years essay questions at the night sessions, right? And okay through the answers ටික මම වෙනම වීඩියෝ එකක් විදිහට එවනවා, right? ඕක ඔක්කොම කම්ප්ලීට් කරන්න. ඔය questions ඔක්කොම කරන්න හරි. first question එක අපි අද දැන් discuss කරනවා. ඕකේ through questions වල answers ටික review වීඩියෝ එකක් විදිහට මම එවනවා, right? ටිකක් බලන්න. Let's do the 2011 question. 2011 question. लेवन क्वेश्चन ला मुलिंग ළමයි ඔය සෙක්ෂන් ඉන්ඩෙල්ටා ජී වලින් ආපු පළවෙනි ක්වෙස්චන් එක ඒ රිසල්ට් 2011 සිම්පලස්ට් ක්වෙස්චන් එක අර ඊමන් ක්වෙස්චන් මෙතනදි කතා කරනවා මොකද ඒක අර මේ තියරිස් කියන පොඩි සිම්පල් අයිඩියා එක ගන්න පුළුවන් නිසා how these things will be used in a question. Question ekrana. Sure. හරි අපි කරමුද ළමයි? හරි. Let's do the 2011 question. Hard. So you have this reaction, right? So N2 gas reacting with 3 of H2 gas, giving you 2 of NH3 gas, no? Right? Some enthalpy of formation, delta F values as well as entropy values are given for N2, H2 and NH3 for all the components in your equation, right? So first thing, calculate delta H naught value for the above reaction 21 Celsius, right? First thing is that. Calculate the delta H naught value, right? Calculating delta H naught R, right? That's the first thing we are doing, right? So as formation enthalpies of all the components of the equation is known, right? Formation enthalpies of all the components of the equation is not actually known, right? So these are reference forms. So reference forms means those carry 0 delta H naught F values, and this value, this guy is with a value, right? Anyway, all the values are given, so that all the delta H naught F values of all the components are known, so that we can come up with delta H naught R with the use of this equation. Delta H naught F of products minus delta H naught F of reactants, right? No? So products, we have NH3. So delta H naught F of NH3 is given as minus 46.1, but we need to produce 2 moles of that thing, right? Not 1, just 2. So 2 into minus 46.1. That is the formation enthalpy of NH3 gas, right? Minus the reactants. So reference forms, that means 0, no? 0 plus 0. So altogether kilojoules per mole, right? So this value coming up as minus 92.2 unit is kilojoules per mole, right? No? It's clear, right? It's simple stuff. Problem number 2. Calculate delta S naught value. So today we have learnt about delta S naught. Calculating delta S naught R. So to calculate delta S naught R, only one equation available in our syllabus. That is this. As entropy is kind of a state function, delta S naught R can be written as S naught products minus S naught reactants. As S naught values are given, you need to come up with delta S naught value, right? You need to come up with the delta S naught equation as S naught values are given, right? If the naught values are given, always equation should be written with the naught. If values are given without the naught, the equation should be written without the naught, right? Keep that in mind. All right? Naught values නම් දීලා තියෙන්නේ note එකත් එක්ක තමයි equation එක ලියන්න ඕනේ. Naught values නැතුව දීලා තියෙනවා නම් equation note values නැතුව ලියන්න ඕනේ. නැත්තම් වට වැරදි දාන්න. Right? Let's apply the numbers. As products, only the NH3 is appearing. NH3's entropy value is value is 192.3, but such 2 are appearing, right? So 2 into 192.3 for the 2 of NH3's. This is the reactants. So this is the product's entropy value minus reactants value. You need 1 N2 is there, so that is 191.5 plus 3 of H2s are there. So 3 into H2's value is 130.7. 130.7. Right? Altogether you need to come up with the unit. Then it is joules per Kelvin per mole. Let's apply the value here. Right, value. So 2 into 192.3 minus 191.5, right? No? Minus 3 into 130.7. Value is given as minus 199. So answer coming up with joules per Kelvin per mole. That is the normal unit used with the delta S naught values, right? Okay. Next one. Let's come up with the Roman number 3. Write the expression related to the chemical reaction. Write the expression expression to relate. Write the expression to relate delta G of a chemical reaction to its delta H and delta S, right? Okay. What is the expression there? Delta G is equal to delta H minus T delta S. This is Roman number 3, part 1. Part 2. The make a note because they are asking you to come up with the ratio between delta G, delta H and delta S. Not between the delta G naught, delta S naught and delta G naught, H naught. They are asking just to write the ratio between delta G, delta H and delta S. The note them. You can't write notes there. So then they are asking calculate delta G naught. Calculate delta G naught then asking. So as they have asked you to calculate delta G naught, the equation should be written with the notes. Right? Alright. So let's apply these values. Delta H naught coming up as minus 92 kilojoules per mole minus T is a temperature, that is 25 Celsius. That means you need to apply that thing in terms of Kelvin. So that is 298 Kelvin into S naught, delta S naught, that is minus 199. 199 is actually coming up as joules per Kelvin per mole, but we need to come up with the same dimensions, same units, so that it should be converted to kilojoules into 10 to the power minus 3 kilojoules per Kelvin per mole. Now simplify the stuff, right? So let's come up with the answer, right? Here this minus becomes positive, minus becomes positive, and Ks will cancel off, right? Ks will cancel off, so that this value also, this section also coming up as kilojoules per mole, right? So let's simplify the stuff. This is going to be a positive value. 298 into this 10 to the minus 3. This value becomes, this whole section becomes plus 59.302, and you have some minus 2.2. No? So it is 32.89, no, minus. Let's take it as 9. Right? Okay. Right, that's it. And they are saying calculate delta G for the variation, right? That's all what they are asking. But let's do a bit more with this question. So if they have asked you to comment on the spontaneity of this reaction at 25 Celsius, 25 වල spontaneity ගැහුවොත් කොයි වගේ කතාවක්ද කියන්න පුළුවන්. So right, I'll do a bit more about this one, right? වැඩිපුර කාරණා ටිකක් හරි. Right, predicting the spontaneity at 25 Celsius. වැඩිපුර ටිකක් අපි ඉගෙනත් දේවල් එක. So how to comment? So delta G is coming up as a negative value. So we can say as delta G is negative, you can say reaction is spontaneous. At 25 Celsius. That is how you are supposed to answer if they have asked you to predict the spontaneous nature or spontaneity at 25 Celsius. හරිනේ? දැන් ඊළඟ questions එකක් දුව අහනවා හොඳේ. ඔයාගේ ඊළඟ 2011 තියෙන ඉදිරි questions ටික කරද්දී අහනවා. right? හරි. ඒක කරන්න. තව පුංචි දෙයක් කතා කරමු මේ කාරණාත් එක්ක. අද අපිට කතා කරන අන්තිම කාරණේ. දැන් මෙහෙම දෙයක් අහන්න පුළුවන් ළමයි. හරි? දැන් මෙහෙම දෙයක් අහන්න පුළුවන්. There could be a question like this. They will ask you a question, at which temperature the reaction starts to occur spontaneously. Such kind of question could be asked. BC5 is spontaneous we don't know, right? But there can be a question asking you to find the temperature at which the reaction starts to occur spontaneously, right? Okay, let's discuss about that thing as well. Finding the temperature. I'll write it here. I need some space for that, right? Okay. Finding the temperature at which reaction start to occur spontaneously. කොයි temperature එකේදී reaction එක spontaneously පටන් ගත්ත කියලා අහන්න පුළුවන්. දැන් මේ spontaneous නේ. හරි ප්‍රශ්නයක් අහන්න පුළුවන්. කොයි temperature එකේදී reaction spontaneously පටන් ගත්ත කියලා. නැත්නම් කොයි temperature එකකින්ද reaction එක non spontaneous වෙන්නේ කියලා. දෙකම එකයි හරි. හරි කොහොමද කරවන්නේ? It's like this නේ. The idea is this. So if you think of the delta G, gives free energy change, right? Let's say this is the negative side and this is the positive side, right? This is the 0, right? If delta G value is positive, it is non-spontaneous. If delta G value is negative, the reaction is spontaneous. So reaction starts to occur spontaneously when delta G becomes 0, right? When delta G is 0, right? That is where the reaction starts to occur spontaneously. It's like this now. So when delta G is a negative value, it is spontaneous. When delta G is a positive value, it is non-spontaneous. Reaction will convert spontaneous to non-spontaneity when the delta G is 0. Or reaction converts from non-spontaneity to spontaneity, right? At delta G 0, right? Okay, na? So this is where reaction converts from spontaneity to non-spontaneity, or non-spontaneity from spontaneity. Right? Or reaction start to occur spontaneously when delta G is equal to 0. So using the values at the equation, when delta G is equal to 0, you can come up with the temperature, right? So that means delta H minus T delta S at that point is equal to 0. So H is minus 92.2. Right, let's subdue the T, right? What we need to find is T. So that T is equal to delta H over delta S. B comes to the other side now. That means minus 92.2 kilojoules per mole divided by delta S value is minus 199 in terms of kilojoules to minus 3 kilojoules per Kelvin per mole. So you will come up with the answer there. Let's come up with that answer. That will give you a temperature in Kelvin. Nah? So what you need to do is 92, this 3 comes to top, right? Divided by 463.3. So this is the temperature at which reaction starts to occur spontaneously, right? If the temperature is less than this, reaction is spontaneous. If the temperature is less than this, reaction is spontaneous. If the temperature is greater than this, reaction becomes non-spontaneous. With higher temperatures, with higher temperatures as delta S is negative, with higher temperatures this whole stuff becomes positive. With highest temperatures, this positive stuff increases, so that the sign of delta G becomes positive with high temperatures. Right? If the temperature is lower than this value, definitely reaction occurs spontaneously. Right? Temperature meter value is more than this. May value is positive value. It's a positive, may sampurna kya positive value one, may negative nisa. This whole stuff is a positive. Temperature value is positive. Positive value is win karna. Delta G positive is to non-spontaneous. Right? So with temperatures lesser than this, the reaction happens spontaneous. Right? So what we can say is, with temperatures, right, lesser than or equal to 463.3 Kelvin, reaction happens spontaneously. Without supplying energy from the outside, reaction will occur. Right now? ඒ වගේ ප්‍රශ්නයක් ඒ වගේ මට්ටමට යනවා අහන්න පුළුවන්. හරි. ඉතින් ළම ඉතුරු questions ටිකත් කරන්න. හරි කරලා කරන්න ඊට පස්සේ මේ මම answers ටික ගවන්න වීඩියෝ රිවිව් එකක් විදිහට එකක් බලන්න. හරි. answers ටික බලන්න. ඊට පස්සේ ඔයාගේ revision note එකේ තියෙන අන්තිම අවුරුදු 5 questions ටික ඒ ටිකත් කරන්න. ඒ ටික අපි කතා කරමු night session එකේදී හෙට. හරිද? ඕගොල්ලගේ electrode chemistry වල MCQs ටිකට answers ටික අපි වීඩියෝ එකකදී වන්න. right? ඒක බලන්න. හරි ඒත් රෝඩ් එකේ අර last 5 years වල questions ටික answers ටික අපි videos එකේ දෙවන්න. ඒක බලන්න. මම last day class එක miss වෙච්ච නිසා. හරි නේද? ඉතින් ඔහොම තමයි වැඩි shape නේ. ඉතින් ළමයි අපි next month එකේ right full papers වලට last වෙනවා. හරි ඒ ගැන announcement එකක් දාන්න group එකේ. හරි එකක් පොඩ්ඩක් බලන්න. right next month එකේ full papers වලට යනවා. right හරි නේද? අපි එතන goodbye then. See you next week.